Good evening, good evening, good evening, good evening, GW soldiers. How are you? I welcome all of you. I welcome all of you to this Jam series revision through questions. Yes, I'm going to discuss the most expected questions of basic thermodynamics, which belongs to most important topics. What I'm going to do is I will be telling you what is the most important topic in this particular subject, basic thermodynamics, and then we are going to solve the question related to that topic. Are you ready? Are you excited? Type in chat box. Yes sir, we are excited, and mark your attendance by typing present sir and your name. So yes, we are going to start this session. Tomorrow, Approved sir will take engineering mechanics at the same time, 4 p.m. Yes, we are ready. We are ready. This is a team. Yes, we are going to teach each and every student of this entire country. Don't worry. Don't worry. Chalo, let's start. Let's start, my friends. And whatever the important topic I'm going to give you today, I'm telling you question will be coming from there. Either you are writing GATE 2023 mechanical or GATE 2023 XE, you are going to see lots of questions from these topics. If you are writing GATE XE, of course in mechanical you will be having 3-4 questions or 2-3-4 questions, whatever. Chalo, one of the topic which is a very important for GATE point of view is displacement work interaction for various standard processes. You must know the formulas of displacement work for isobaric process, isothermal process, isentropic process, polytopic process. So let us solve one question quickly. Yes, Prashant, don't worry. I'm telling you, whatever the topics I'm going to tell you, that is, these are very important for mechanical point of view, XE point of view. Yes, let us start solving the question. And look at here. I will be telling you the type of question and weightage of the question. NAT, numerical answer type question of 2 marks. Let us read the question. A perfect gas is having volume of 0.024 meter cube at 700 kilopascal pressure and 95 degrees Celsius temperature in a piston cylinder arrangement. What is given in the question? I'm having a piston cylinder arrangement. In that piston cylinder arrangement, there is some perfect gas. Now, the initial volume of the perfect gas is 0.024 meter cube. Initial pressure is 700 kilopascal and initial temperature is 95 degrees Celsius. If you convert into Kelvin, 273 you need to add. Now the gas undergoes a reversible, non-flow, polytropic expansion process according to the relation PV power 1.2 is equal to constant until the pressure of the gas reaches to 70 kilopascal. What is happening basically? Perfect gas is undergoing some polytropic process which is given by the relation PV power 1.2 is equal to constant until the final pressure after polytropic expansion is 70 kilopascal. After this, the gas undergoes a reversible isobaric heat addition process until the gas temperature reduces to its initial temperature. So according to the question, what is happening? First we are having polytropic expansion, and after that we are having isobaric heat addition process. That means 1 to 2 is polytropic expansion process, and then 2 to 3 is isobaric heat addition process. and it is given that the final temperature after isobaric heat addition process is equal to initial temperature T1. The total work done is a dash kilojoule, round off to 2 decimal places, take capital R. What is the capital R over here, beta? Anyone in the class can tell me what is this capital R over here? Type in chat box. This is your characteristic gas constant, 272 joule per kg per Kelvin. Now, first of all, I will be writing the data for you. But today, I'm telling you, solve all the questions along with me. Each and every question is brand new question, most expected question. So don't miss. So let me write everything whatever given in the question. First in the question, he has given perfect gas having volume of 0.024 meter cube. So initial volume is given 0.024 meter cube. Very good. At 700 kilopascal, P1 is given 700 kilopascal. Initial temperature T1 is how much, beta? Initial temperature T1 is how much? 95 degrees Celsius. Can you tell me, if I want to convert into Kelvin, how much Kelvin? Just add 273. So basically, 368 Kelvin. Very good. Now, the gas undergoes a reversible non-flow polytropic expansion process according to relation PV power 1.2 is equal to constant. So 1 to 2 is the polytropic expansion process, PV power 1.2 is equal to constant. Anyone in the class can tell me what is the polytropic index? Quickly. Anyone in the class can tell me what is the polytropic index? What is the value of N? You will be requiring the value of N. Yes. N is 1.2. Beautiful. Until the pressure of the gas reaches to 70 kilopascal, P2 is given 70 kilopascal. And remember one more thing. This is your expansion, clearly given in the question. Let me write here itself so that you are not getting confused. This is expansion. Chalo. Now, after this, the gas undergoes a reversible isobaric heat addition process. So basically 2 to 3 is isobaric heat addition process. Perfect. Until the gas temperature reduces to its initial temperature, T3 is equal to T1. So basically 368 Kelvin. The total work done is a dash kilojoule, round off to 2 decimal place. W123 he is asking in kilojoule, round off to 2 decimal place. Capital R is given in the question, 272 joule per kg per Kelvin. Now, I hope everyone is crystal clear with the data. Everyone is, namaste beta, namaste. I hope everyone is crystal clear with the data. Data is clear to everyone. Data is crystal clear to everyone. Type in chat box beta. Acha, now, before I start solving this problem, I want to see how many of you will be able to draw a correct PV diagram. Honestly, I'm telling you, you have to draw the PV diagram right now. Draw and check whether you have drawn the correct PV diagram or not. I want to see how many of you will be able to draw the correct PV diagram. On the vertical axis, take pressure. On the vertical axis, take pressure. On the horizontal axis, take volume. Look at here. On the vertical axis, I am taking pressure. On the horizontal axis, I am taking volume. Of course, pressure I will be taking in kilopascal. Volume I am going to take in meter cube. So look at here. Let us suppose this horizontal line. Let us suppose this horizontal. Oh, what a beautiful horizontal line. Let us suppose this horizontal line is representing pressure P1, which is basically 700 kilopascal. Let me say this vertical line is representing the initial volume, which is given in the question how much? 0.024 meter cube. So basically this is the initial state. Now what is happening? I am having polytropic expansion process till the pressure becomes 70 kilopascal. Till the pressure becomes 70 kilopascal. So this is P2, basically 70 kilopascal, and of course since I am having polytropic expansion, V2 will be greater than V1. Let us suppose this is a final volume V2. So you must be able to understand this is the state 2. So the process PV power 1.2 is equal to constant is something like this. Now what is going to happen? I am having isobaric heat addition process. Anyone in the class can tell me, if I am having isobaric heat addition process to a closed system, what will happen to the volume? What will happen to the volume? What is going to happen to the volume? Can I say volume is going to increase because isobaric heat addition means isobaric expansion process, so 100% volume is going to increase. So you can observe the process 2 to 3 will be something like this. The process 2 to 3 will be something like this. Isobaric heat addition process. Indirectly isobaric expansion. So yes, this is the final volume V3. This is the final state 3. I hope everyone has drawn the same diagram. Now listen carefully. Are you able to understand what he is asking in the question? He is asking the total work interaction. Now, what is the total work interaction? Can I say total work interaction is a W 1, 2, 3. Now, if he is asking total work interaction, I hope you are able to understand. I need to find W1 to 2. I need to find W2 to 3. And I need to add both of them. Now, before I start solving, I'm asking a very, very, very fundamental question to you people. Can you tell me W1 to 2 will be positive or negative? W1 to 2 will be positive or negative? W1 to 2 will be positive or negative? Come on everyone. W1 to 2 will be positive. Why are you saying W1 to 2 will be positive? Because during the process 1 to 2, the volume is increasing, and 100% if a volume is increasing, displacement work must be positive. Displacement work must be positive. There is no doubt. Displacement work must be positive. What about W2 to 3 beta? W2 to 3 will be positive or negative? 100% in W2 to 3 also. If the process 2 to 3, you see it is isobaric heat addition process, isobaric expansion process, volume is going to increase. Displacement work must be positive. And if displacement work must be positive, W2 to 3 must be positive. Now you tell me, if W1 to 2 is a positive, W2 to 3 is positive, W1 to 3, total work interaction must be positive or negative? 100% total work interaction must be positive. So If anyone is getting the negative answer, it is a wrong, re baba. It is a wrong, re baba. You must get the positive values of W1 to 2, W2 to 3, and ultimately when you are adding both of them, W1 to 3 will be positive. I hope each and everyone is a crystal clear till here. I hope each and everyone is crystal clear till here that the answer will be coming positive. Now there is calculation. That's it. Now there is calculation. Now, how to find W1 to 2? Look at here. It is a polytopic process. For polytopic process, what is the formula we know? P1 V1 minus a P2 V2 upon n minus 1. This is the formula of displacement work which I have given you for the polytopic process. P1 is given in the question. V1 is given in the question. P2 is also given in the question. What is unknown here, beta? What is unknown here? V2 is unknown. Array, he is asking W1 to 3. Look at here. There is nothing to mug up. Just read the question carefully. I'm telling you how to strike the question in examination, how to attempt the question in examination. I came to know he is asking W1 to 3. I know if I want to find W1 to 3, find W1 to 2, find W2 to 3, add both of them. So first I'm finding W1 to 2, P1 V1 minus P2 V2 upon n minus 1. V2 is unknown. How to find this V2? How to find this V2? P1 V1 power 1.2 is equal to P2 V2 power 1.2, because he has given PV power 1.2 is constant during the polytopic expansion process. So from here, if I want to find V2, V2 will be coming a P1 by P2 whole power 1 by 1.2 into V1. So V2 is equal to what? 700 kilopascal divided by 70 kilopascal power 1 by 1.2 into V1. V1 is how much? 0.024 meter cube. But anyone in the class can tell me what is the value of V2 we are getting? Pata, tell me in the chat box. Pata, tell me in the chat box what is the value of V2 you people are getting. Can I say 0.16351? 0.16351 meter cube. Excellent. The moment you are getting V2, now you can easily find the displacement work 1 to 2. P1 700 kilopascal, V1 0.024 minus a P2 70 kilopascal into V2 0.16351 divided by n minus 1. 1.2 minus 1. So what is a W1 to 2 we are getting, beta? What is the displacement work we are getting during the polytopic expansion process? Yes. Oh, Jia, Lala, Arihant, Amit, Samir, Tripat. Oh my God, what a beauty. Beautiful, beta, beautiful. 26.7715. 26.7715 kilojoule. I got W1 to 2. The question is not over yet. I need to find W2 to 3 also. Now, how to find W2 to 3? It is clearly given. The temperature after isobaric heat addition is equal to the initial temperature, that 368 Kelvin. So look at here. W2 to 3, P delta V na. So P2 delta V, final volume minus initial volume. But I would not write in terms of pressure and volumes because I know the temperature, final temperature. So what I'm going to do is, I will write like this: MR T3, which I know, minus T2. Now look at here. How to find MR? Array, use ideal gas equation. P1 V1 is equal to MR T1. And if P1 V1 is equal to MR T1, P1 V1 by T1 will be giving me MR. T3 is a T1 minus a T2. Now, if I want to find W223, there is only one unknown on the right hand side. What is unknown on the right hand side? Any intelligent student of the class can tell me. If I know that particular variable, if that particular value, I will be getting the answer. Yes, T2 is unknown. T2 is unknown. I want to find T2 now. How to find this T2? Look at here. I know the value of N. I know the value of P1, P2. So can I write P power 1 minus N upon N is equal to constant. P1 power 1 minus N upon N is equal to T2 power 1 minus N upon N. From here, I will be finding T2, and T2 will be P1 by P2 whole power 1 minus N upon N into T1. P1 700 kilopascal divided by P2 70 kilopascal. 1 minus 1.2 by 1.2. T1 was 95 degrees Celsius, which means 368 Kelvin. Anyone in the class can tell me what is the value of T2 you are getting, beta? What is the, in a single question, I will be solving multiple questions. Tell me what is the value? Vineet, very good. 250.715. Yes, T2 is 250. Yes, very good, very good. 0.715 Kelvin. This is the value of T2. Once I got T2, now there is nothing in the question. Look at here. W223 is equal to P1 700 kilopascal into V1. If I'm not wrong, B1 is a 0.024 meter cube divided by T1, which is 368 Kelvin. T1, T3 is T1, 368 minus 250.715. Any intelligent student of the class can tell me what is the W223 you people are getting? What is the value of W223 you people are getting? Come on everyone, tell me the answer. What is the value of W223 you people are getting? Quickly. 5.3543. 5.3543 kilojoule. But I got W223 also. Now, W123 is basically W122, which is 26.7715 plus 5.3543. So W123 is how much? 32.1258 kilojoule. Are you getting something like this? Are you getting something like this? If you are getting the correct answer, what is the correct answer? 32.1258. So if I want to write 32.13, let me give 32.13, let me give. I want each and every one of you to make the complete chat box red with your hearts if you have done this question by yourself or along with me. If you are able to solve this question, by yourself or along with me, make this entire chat box red with your heart symbols. Re Baba. What a beauty, what a beauty. I will be giving the range also. For this question. The range is 30.13 to 34.13. I will be giving you the range also. Oh, what a beauty, what a beauty, what a beauty. So my friends, such questions can come in examination where you need to apply the standard displacement formulas to get the answer. Chalo. Next important topic. What is the next important topic? Heat interaction for various processes. Yes. There are so many standard processes. Isochoric process, isobaric process, isothermal process, polytopic process, leave it. But at least you should know all these formulas. Isochoric process, how to calculate the heat interaction. Isobaric process you should know. And isothermal process you should know. And yes, there might be chances they can ask you, if the process is polytopic process, how to calculate the heat interaction. So another very, very, very important topic, and I'm telling you, you write your GATE 2023, whatever the important topics I'm giving you, you'll be getting the questions from here only. Chalo, let us go to the next question. MSQ, oh my God, this is MSQ. Multiple select question, 1 mark MSQ. Air having a mass of 2 kg is enclosed in a variable load piston cylinder arrangement at a 600 kilopascal pressure, 200 degrees Celsius temperature. I'm having a variable load piston cylinder arrangement. Inside that variable load piston cylinder arrangement, I'm having air. The mass of air is given 2 kg. The initial pressure of air is given 600 kilopascal. The initial temperature of air is given 200 degrees Celsius, which means 473 Kelvin. The gas undergoes, gas means air. Air undergoes a reversible isothermal heat addition process until the final pressure of the air becomes 80 kilopascal. Okay. So what is happening? Air is undergoing a reversible isothermal heat addition process until the final pressure of the air becomes 80 kilopascal. Which one or more of the following statements are correct? Option A, during the process, volume of the air decreases. Option B, during the process, volume of the air increases. Option C, the work interaction during the process is 345.05 kilojoule to 349.05 kilojoule. Option D, the heat interaction during the process is 545.05 kilojoule to 549.05 kilojoule. Champu. I started giving the answer. This is MSQ, Baba. It is not MCQ. One or more than one statements can be correct. When I'm asking you the question, then only you give me. First of all, you tell me one thing. I started giving the answer. Okay. First of all, you tell me. If I'm having a closed system consisting air, reversible isothermal heat addition process. Can I say reversible isothermal heat addition process is basically isothermal expansion process only? So 100% volume is going to increase. 100% volume is going to increase. How? I will be telling you. First, let me write the data, then we will be solving the question. Air having a mass of 2 kg. Mass is given. 2 kg is enclosed in a variable load piston cylinder arrangement at a 600 kilopascal. P1 is given 600 100 kilopascal. T1 is given 200 degrees Celsius. If I add 273, I will be getting in Kelvin, which means a 473 Kelvin. Okay. The air undergoes a reversible isothermal heat addition process until the final pressure of air becomes 80 kilopascal. P2 is 80 kilopascal. Okay. Now statements. First of all, anyone in the class can tell me what will be delta U for air in this case? What will be delta U for air in this case? Change in internal energy for air. देखो, according to first law of thermodynamics, for a process I can write Q is equal to W plus delta capital E. Right? Of course, I am having a stationary system. So delta capital E can be written as a delta capital U. So Q is equal to W plus delta capital U. Air is undergoing isothermal process. If air is undergoing isothermal process, the internal energy, listen the statement carefully, Baba. For an ideal gas, internal energy is the function of temperature only. Here, I am assuming air is behaving as an ideal gas. It is undergoing isothermal process. So temperature is constant throughout. 100% internal energy will be constant throughout. Delta capital U will be 0. So Q is equal to W. Now, if Q is given positive heat addition, so W will be automatically positive. Displacement work is positive. That means volume increases. So can you tell me, out of statement A and statement B, which one is correct? C and D we will see, beta. But out of statement A and statement B, I want you people to answer me which statement is correct. A is wrong. During the process, volume of the air increases. Now let us talk about work interaction. What is the formula of displacement work for isothermal process? W1 is equal to, if you remember, C ln V2 by V1 is equal to C ln P1 by P2. Which formula I am going to apply? V2 by V1 or P1 by P2? 100% P1 by P2, because they have given me P1, P2. So W1 is equal to C ln P1 by P2. Now what are we going to write in place of C? Mass I know na. If mass is known, temperature is known, MRT1 I will be writing in place of C, MRT1 ln P1 by P2. So yes, W1 is equal to M. M is how much? 2 kg. R. He is asking the answer in kilojoule. So R I am going to write in kilojoule per kg per Kelvin, which is basically 0.287 for air. T1 is how much? 473 Kelvin. Ln P1 by P2, 600 by 80. Now anyone in the class can tell me what is the value of W1 you are getting from here? What is the value of W1 you are getting from here? Anyone in the class can tell me? 547.05. Absolutely correct. W1 is 547.05 kilojoule. This is the magnitude. This is basically the displacement work during the isothermal heat addition process. Let me see whether it is matching with the option statement C or not. No. This is wrong, Re Baba. No. In statement D, he is talking about heat interaction. Are champo, for an ideal gas undergoing isothermal process, whatever is the displacement work, whatever is the work interaction, that is your heat interaction, because delta U is going to be 0. So 547.05 kilojoule is your heat interaction, provided you are having a stationary system. There is no change in kinetic energy and potential energy of the closed system. 547.05. Yes, D is correct. So the correct answer is B, D. How many of you are able to solve this problem? Yeah, make the entire chat box red with your hearts if you are able to solve this beautiful problem. Oh my God, what a beauty, what a beauty, what a beauty! The range of option D, statement D, is 545.05 kilojoule to 549.05 kilojoule. What a beauty! And we go for the next question. I'm telling you, in GATE 2023, you see, you write the exam on 4th Feb, you write the exam on 11th Feb, you'll be getting the questions from here. I want to solve one more question. And I'm telling you, beta, P2 is 80, na? P2 is 80. P2 is 80, re baba. Thank you so much, beta. P2 is 80, na? Now, I want to solve one more question. Now, this is MSQ. I will be focusing more on MSQ and NAT because I know you people are having the trouble in solving these questions. So, MSQ 2 marks. Be very, very, very careful. A stationary piston cylinder arrangement contains 0.8 kg of nitrogen gas initially at 100 kilopascal pressure and at 27 degrees Celsius temperature. I'm having a stationary piston cylinder arrangement. In this stationary piston cylinder arrangement, I'm having a nitrogen gas filled. The mass of nitrogen gas is given 0.8 kg. The initial pressure of the nitrogen gas is given 100 kilopascal. The initial temperature is given 27 degrees Celsius, which means 300 Kelvin. Now, the gas undergoes a quasi-static, basically internally reversible polytopic compression process. Okay. The nitrogen gas is undergoing quasi-static polytopic compression process. PV power 1.3 is equal to constant. N is given in the question. Polytropic index 1.3. Until the volume of the gas reduced to half of the initial volume. Of course, if in the question he is saying compression, the volume has to decrease, and the volume is decreasing in such a way that final volume is half of initial volume. V2 is V1 by 2, or you can say 0.5 V1. Which one or more of the following statements are correct? In statement A, he is asking the final temperature of the nitrogen. In statement B, he is asking final temperature of the nitrogen. In statement C, he is asking the magnitude of work interaction during the process. In statement D, he is asking magnitude of heat interaction during the process. Good evening, beta. Good evening. Now, let us attack on the part 1 after writing the data. Hello, let me write the data for you. Look, I'm going to solve step by step for you people. Meanwhile, you start solving. Mass is given. First of all, nitrogen gas is given, hai na? What is the mass of nitrogen gas given in the question? 0.8 kg. 0.8 kg. Initial pressure is given 100 kilopascal. Initial temperature is given 27 degrees Celsius, which means 300 Kelvin. Nitrogen gas is undergoing polytropic compression process given by PV power 1.3 is equal to constant. Until the final volume is half of initial volume. Okay, till here I am able to understand each and everything. Done. In statement A and B, he is asking final temperature T2. Yeah, how to find T2? Come on, GW soldiers, help me. How to find T2? He is asking final temperature. Look, in the question, I know what is the value of N. The moment I know the value of N, the moment I know V2 is half of V1, can I write something like this? T V power N minus 1 is constant. Come on, tell me beta. Yes, I'm having polytopic process. Initial temperature is known. The relation between V2 and V1 is known. So I will be applying this formula to find T2. So T1, V1 power N is 1.3 minus 1 is equal to T2, V2 power N minus 1. From here, I will be able to calculate T2. T2 is what? V1 by V2 power 0.3 T1. Yeah, V1 by V2 will be 2 na. If V2 is half of V1, so V1 by V2 will be 2. 2 power 0.3 into 300 Kelvin. Can you tell me what is the final temperature you are getting, beta? What is the value of final temperature you people are getting? Please help me with this. What is the value of T2 you people are getting? 369.343. Very good, beta. 369.343 Kelvin. Excellent. Beautiful. This is the final temperature of nitrogen after polytropic compression. Out of A and B, which one is matching? I think A is matching. Yes. Out of A and B, A is correct, B is wrong. Done. Now the next part, the magnitude of work interaction. How to find the magnitude of work interaction? How to find the magnitude of work interaction? For polytropic process, we know one thing. Displacement work 1 to 2 is equal to P1 V1 minus P2 V2 upon N minus 1. But I'm not going to use this formula. Already I know T2. So what I'm going to do is, I will be using the formula where I'm having the temperatures. MRT1 minus T2 upon N minus 1. Now look at here. T1 is known. T2 is known. M is known. N is known. Capital R is unknown. Chhapa Ramesh, Manoj, very good. Capital R is unknown. How to find capital R? But at the moment they have given the gas, you know, the moment they have given the gas in the question, nitrogen gas, you must be able to calculate capital R, and if required, you must be able to calculate Cp and Cv. Look at here. Okay, if examiner is kind-hearted like me, he can give you, okay, let us take Champu this R also, Cp, Cv also. Lekin, I'm telling you, if examiner is a cunning, he will not give you capital R, he will not give you Cp, he is not going to give you Cv. And here, when I was framing this question, I became the cunning examiner. Capital R you can find universal gas constant divided by molar mass of nitrogen. So yes, W122 can be written as, in place of capital R, I will be writing R bar upon molar mass of nitrogen. And now if Champu don't know the molar mass of nitrogen, Champu will be getting swaha. Champu will be getting swaha. Champu, molar mass of nitrogen you don't know. W122 is equal to mass of nitrogen given in the question 0.8 kg. I need to find capital W in kilojoule. So let me write R bar in kilojoule per kilomole per Kelvin, 8.314 kilojoule per kilomole per Kelvin. T1 minus T2 300 minus 369.343 Kelvin divided by what? Molar mass of nitrogen 28 kg per kilomole. N is 1.3, 1.3 minus 1.3. What is the value of W122 you are getting? What is the value of W122 you are getting? After solving, good evening beta, good evening. After solving, what is the value of W122 you people are getting? Come on everyone, tell me in chat box. Positive or negative? It should be negative, na? Arey, it is coming positive or negative? First of all, you tell me this part. Sumit, very good. Minus 54.906 minus 54.906 kilojoule. Acha. Anyone in the class can tell me? Yes, sir. With 100% confidence, we can say answer of displacement work will be negative only. When we are solving, this must come negative only. How can you say? Can you tell me? Can you tell me with 100% confidence? Yes, sir. When we are solving for W122, it must come negative. It must come negative. Can you tell me? Can you tell me? By seeing the question, I was aware that when I'm solving W122, it will come negative. I forget about magnitude and all that I know. If in the question he is asking magnitude, you have to write positive part only. But what I'm saying is, by seeing this question, can you tell with 100% confidence, sir, displacement work will be coming negative only when we are applying the formula? Clearly in the question he has written. Compression process. The moment he is saying compression process, you are aware that volume is decreasing and 100% displacement work will be coming negative. Now, the magnitude of work interaction during the process is, of course, magnitude will be 54.906. Yes, C is correct. Tell me beta, can I say C is correct? C is correct. Very good. C is correct. Very good. Now, in statement D, he is asking heat interaction during this process. But for polytropic process, if you are able to recollect, Q122 is equal to gamma minus N upon gamma minus 1 W122. This is the formula. This is the relation between heat interaction and work interaction for the polytopic process. Now, Q122 will be how much? Gamma. Gamma for nitrogen diatomic gas, I am taking 1.4 minus 1.3 upon gamma 1.4 minus 1 W122. Just now I have calculated. Minus ka 54.906. Can you tell me what is Q122 you people are getting after solving this? What is the value of Q122 you people are getting after solving this? Yes, minus ka 13.7265 kilojoule. This is my Q122. Let us check. Can I say this is also correct? Statement D is also correct. So the answer of this question is D Delhi is also correct. So answer of this question is A, C, D. How many of you are getting the same answer A, C, D? How many of you are getting the same answer A, C, D? No. Yes. Oh, beautiful, beautiful, excellent. Now here I want to ask you one more question. Can you calculate delta U also? Let us suppose I am adding one more question. What is the change in internal energy? Anyone in the class can tell me what is the change in internal energy you people are going to get? Can you calculate the change in internal energy also? You already calculated W, you already calculated Q. Can you tell me what is the delta capital U you are going to get? Delta capital U, change in interim. I know so many of you will be doing the mistake over here. Can you tell me what is the delta U you people are going to get? It will be negative or positive. It will be negative or positive. Yes, yes, Vinit. Yeah. Oh my, this is the beauty of thermodynamics. This is the beauty of thermodynamics. You people are getting confused. Some people are saying negative, some people are saying positive. This is what I want to see. Look at here, beta. A single question is getting converted into multiple questions. Look at here. If I'm asking you delta U, basic is Q is equal to W plus delta capital U. So delta capital U is equal to Q minus W. Delta capital U, Q is how much? Minus 13.7265 minus W is how much? Minus 54.906. Delta capital U is coming how much? What is the change in internal energy? 41.1795. Now, anyone with 100% confidence, anyone with 100% confidence can tell me, sir, I was aware. Sir, I was aware. 100% delta U change in internal energy will be coming positive. Sir, I was aware. I need not to solve. I need not to solve. Champus will be solving. Champus will be solving, but I was aware delta U will be positive. Array, look at here. When you have calculated for final temperature was coming 369.343, which is greater than T1, which is greater than initial temperature. So what is happening? The temperature of nitrogen is increasing, and if nitrogen is behaving as perfect gas, 100% there is no doubt. 100% there is no doubt, if a temperature is increasing, internal energy has to increase, delta U has to be positive. Delta U has to be positive. So let us suppose in examination he is asking T2 and delta U. He is asking only T2 and delta U. He is not asking W. He is not asking capital Q. Then how to find delta capital U? Array, MCV delta T. MCV T2 minus a T1. T2 you have calculated. T1 you already know. CV is equal to R upon gamma minus 1. That's how you will be getting delta U. And I am telling you, if you are using the formula MCV delta T, you will be getting the same answer. Trust me, you will be getting the same answer. So we go for the next question. Are you ready? So the next most important topic which I'm telling you is application of steady flow energy equation for a nozzle. This question is a due. This question is a due. Anytime you can have the question on nozzle. Yes, a steady flow will be given and they will be asking maybe outlet velocity, maybe outlet area of the nozzle, something like that. So if you people are ready, let us solve the question. Oh my God, again MSQ, 2 marks. Again MSQ, 2 marks. Steam enters steadily in a well-insulated horizontal nozzle with a mass flow rate of 2 kg per second at 30 bar 20 degrees Celsius, where small h is given, small b, a specific volume is given with a velocity of 100 meter per second, Ci is given. But at the moment he is saying W dot well insulated, you must be able to understand Q dot is Sunya. Horizontal means delta P dot is Sunya. So basically he has given the mass flow rate, Pi, Ti, small hi, small vi. Steadily word is used, so m dot I is equal to m dot O, and you can apply steady flow energy equation. Ci is given. The steam leaves the nozzle at 10 bar. Here you are having the space, comma, 200 degrees Celsius. Specific enthalpy at the outlet is given. Specific volume at the outlet is given. Which one or more of the following statements are correct? Look at here, beta. Look at here. The inlet flow area of the nozzle, the inlet flow area of the nozzle is, in statement A, he is asking inlet flow area of the nozzle. In statement B, he is asking exit velocity of the steam at the outlet of nozzle. In statement C also same thing, CO he is asking. In statement D, he is talking about exit flow area of the nozzle. So for answering this MSQ, you have to find AI, you have to find CO, you have to find AO. So let me write the data for you people. Look, I need not to draw the diagram. You are aware how the diagram will look like. Look, maybe there is some champu who don't know. So let me draw for my champu. Yes, I have to take care of my champus also, na? I have to take care of my champus also, re baba. Champu will also clear the GATE exam. Champu will also go to IIT. Champu will also become IITian, re baba. Yes, IITian Champa. My IITian Champa. This is my well insulated horizontal nozzle. Oh, what a beautiful well insulated horizontal nozzle. Let me say the flow is taking place left to right, something like this. So this is your inlet, this is your outlet. Chalo, let me write the data. Steam enters steadily. The word steadily is mentioned in a well insulated horizontal nozzle with a mass flow rate of 2 kg per second. Mass flow rate is given at the inlet. M dot I is given 2 kg per second. Beautiful. What are data? At 30 bar 20 degrees Celsius. PI is given 30 bar. PI is given 20 degrees Celsius. Beautiful. Now, small h 3043.4 kilojoule per kg. 3043.4 kilojoule per kg specific enthalpy at the inlet of well insulated horizontal nozzle. Small v 0.0850. 0.0850 meter cube per kg specific volume at the inlet. So small vi is given. Okay. Now with a velocity of 100 meter per second, Ci is given how much? Ci is given 100 meter per second. Champa. Now the steam leaves the nozzle at 10 bar. PO is given 10 bar. PO is given 10 bar, comma 200 degrees Celsius. So PO is given 200 degrees Celsius. Beautiful. Now small h, small ho 2827.9. 2827.9 kilojoule per kg is small ho. Small VO is given. How much is small VO, Champa? 0.2060. 0.2060 meter cube per kg. Oh my God, lots of data is given. Chalo. Now, inlet flow area. But how are you going to find inlet flow area? Anyone in the class can tell me? How to find inlet flow area? फटाफट से बताओ. Tell me quickly. Inlet flow area, how to calculate? Tell me quickly, beta. Pata party tala tali re baba. Look at here. This formula is coming from fluid mechanics. Mass flow rate is equal to rho AC. Of course, here the C is the average velocity. Mass flow rate, of course, I'm finding at inlet is equal to rho I AI, CI. Rho I is not known, but specific volume is known. So we know specific volume is the reciprocal of density, or in other words, density is reciprocal of specific volume. So it will become AI, CI divided by small vi. I need to find AI. So it will become m dot I small vi divided by Ci. And if I substitute the data, AI is equal to what? Champa! Oh, Champu, don't dare to apply ideal gas equation. Oh my God! Champu is saying, sir, density P is equal to rho RT, sir. Sir, density is equal to P by RT, sir, Pi by RTI. Champu, in the question, they have given steam. They have given you steam. Don't dare to take steam as an ideal gas. You will be getting swaha. M dot I 2 kg per second. Small vi is how much? 0.0850 divided by Ci. Ci is how much, beta? Ci is how much? 100 meter per second. So from here, after solving, how much we are getting? Of course, we'll be getting in meter square. 0.0017 meter square. He is asking in centimeter square. So can I say inlet area of the nozzle is 17 centimeter square? Yaar, ye confirm kar do. Please confirm me this. Can I say AI is a 17 centimeter square? Please confirm me this part. Can I say AI is 17? Yes, yes, Sunil. Very good. Mayank, very good. I am able to get AI, the inlet flow area is, yes, this is correct. This is correct. This is absolutely correct. Now the next part, the exit velocity of the steam at the outlet of the nozzle is how to find the exit velocity. What is coming in your mind? How are you going to find the exit velocity? Of course, I will be applying the steady flow energy equation to find the exit velocity, because the steady flow is given. If a steady flow is given, I'm going to apply steady flow energy equation. Look at here. Can I write according to SFEE, according to steady flow energy equation, Q dot is equal to what? W dot CV plus delta KE dot plus delta PE dot plus delta capital S dot. Now look at here. First of all, it is a nozzle. The moment nozzle is given in the question, 100% W dot CV will be shunya. Now I'm having well insulated horizontal nozzle. If I'm having well insulated horizontal nozzle, can you tell me, if I'm having a well insulated horizontal nozzle, which two terms will be shunya? If I'm having well insulated horizontal nozzle, which two terms will be shunya? Q dot is shunya because I'm having a well insulated nozzle. Of course, there is no doubt delta P dot will be shunya because I'm having horizontal nozzle. Now look at here. What I got? Delta Ke dot plus a delta capital H dot is equal to shunya. If I want to write in per unit mass, delta small Ke plus a delta small h is equal to shunya. Now look at here. I need to find, look at here, one very, very, very important thing I'm going to tell you. Since I need to find the velocity at the outlet, I must write in joule per kg only. I'm writing in joule per kg only. Of course, if you understand each and everything, you can write in kilojoule per kg also, but let's keep it very simple. I'm writing in joule per kg. So what I'm going to get? Half CO square minus CI square. Don't commit the mistake. I'm writing in joule per kg. So whatever small ho, small hi is given in the question, that must be converted into joule per kg. If you are writing the equation in kilojoule per kg, then you have to understand one thing. Here in place of 1 by 2, you must write 1 by 2000. So look at here. Half CO square minus a CI square. CI is how much? 100 meter per second. Small ho minus small hi. Small ho 2827.9 27.9 kilojoule per kg. I have to convert in joule per kg, so I will be multiplying by 1000. HI 3043.4. 3043.4. Now look at here. Since I am writing the equation in joule per kg, I am multiplying this term by 1000 so that this kilojoule per kg will convert into joule per kg. From here, what is the value of CO you people are getting, beta? What is the value of CO you people are getting? What is the value of CO you people are getting? Can I say 664.078? Very good, Vineet. Meter per second. Yes, this is the value of CO which I am getting. This is the value of CO which I am getting. Now you tell me which option is correct, which statement is correct, B or C? Out of B and C, which one is correct? I think B is correct. B is correct. B is correct, C is incorrect. B is right, C is wrong. Now he is asking exit flow area. How to find exit flow area? Array m dot O small VO divided by CO. M dot O small VO divided by CO. If I am having a steady flow, there is no doubt m dot O is equal to m dot I, which is basically how much? 2 kg per second. Yes, 2 kg per second. What is the specific volume at the outlet? What is the specific volume at the outlet? 0.2060. 0.2060 meter cube per kg divided by CO 664.078 meter per second. What is the value of a small HO you people are getting, beta? How much is this? After solving, how much is this coming? If I convert into centimeter square, can I say 6.2 centimeter square? Can I say 6.2 centimeter square? Confirm me this part. Is it 6.2 centimeter square? Yes, very good, very good, very good. Excellent. Excellent. So option D is also correct. So what is the correct answer of this MSQ, beta? What is the correct? Sanjay, tell me, beta. Kalpesh, Mayank, tell me what is the correct answer of this MSQ? Can I say A, comma B, comma D? And if you are able to solve this question MSQ, let us make the entire chat box red with your heart symbols. If you are able to solve, yes, ABD is correct. I hope you are able to solve the questions. I hope you are able to solve the questions along with me or by yourself. Yes, Govinda, very good. Now, I don't know why I'm having this feeling. This year, you will be getting the question from steady flow energy equation. So, either you will be getting on nozzle or the next most important topic, the next most important topic, The application of steady flow energy equation for turbine. Yes, either it is a nozzle or turbine. MCQ. Multiple choice question, 1 mark. What is the question? Steam enters a well-insulated turbine under steady state. The moment steady state is written in the question, you have to understand m dot I is equal to m dot O, because dm by dt of the control volume will be shunya, and you can apply the steady flow energy equation at a pressure of 4 megapascal, velocity of 8 meters per second, and specific enthalpy of 3018.5 kilojoule per kg. So Pi is given, Ci is given, small hi is given. Steam expands and leaves the turbine at a pressure of 0.09 megapascal, velocity of 80 meters per second, and specific enthalpy of 2458.6 kilojoule per kg. Okay. If the mass flow rate of the steam is at 10 kg per second, then the power developed by the turbine is a dash megawatt. Neglect the effect of potential energy. Yes, W dot CV he is asking. So whatever the data is given, let me write for you people. Clearly he is saying a well insulated turbine. In the question it is a clearly given. In the question it is a clearly given well insulated turbine. In the question clearly it is given well insulated turbine. Okay. Under steady state at pressure 4 megapascal, Pi is given. Pi is how much? 4 megapascal. Pi is given 4 megapascal. Velocity of 8 meter per second. Ci is given. Ci is given 8 meter per second. Small hi is given 3018.5. 3018.5 kilojoule per kg. Steam expands and leaves the turbine at a pressure of 0.09 megapascal. 0.09 megapascal. PO is given in the question. CO is given 80 meter per second. CO is given, and I am telling you, please try to understand. Right now we are solving the most expected questions. I am not making it very difficult which cannot come in the examination. I am keeping those questions only which you can have in examination, whether it is easy, moderate or difficult. CO is given 80 meter per second and specific enthalpy of 2458.6. Small ho, 2458.6 kilojoule per kg. Kilojoule per kg. If the mass flow rate of the steam is at 10 kg per second, m dot is given. M dot is given 10 kg per second. Then the power developed by the turbine is a dash megawatt. W dot CV he is asking in megawatt. In megawatt. Neglect the effect of potential energy. Now, but how are you going to solve? How are you going to solve this question? Tell me. The moment you have seen the question, the moment you have seen the data, what is coming in your mind? What is coming in your mind? Can I say we have to apply the steady flow energy equation? Yes, we have to apply the steady flow energy equation. Let us apply the steady flow energy equation according to SFE. Let me write each and everything for you people. According to SFE, steady flow energy equation, I can write Q dot is equal to W dot CV plus delta KE dot plus delta PE dot plus delta capital S dot. Now, anyone in the class can tell me, according to given things in the question. Which two terms are shunya according to given data in the question, given things in the question, which two terms will be shunya? 100% he is saying, 100% he is saying well insulated turbine. Well insulated turbine. So of course Q dot has to be shunya. He is saying neglecting the changes in potential energy, so it is shunya. I need to find W dot CV. So W dot CV plus delta KE dot plus delta capital H dot is equal to shunya. So I can write W dot CV is equal to minus delta KE dot plus delta capital S dot. Now here we need to take the decision whether we want to write in watt or kilowatt. Since he is asking in megawatt, let me write this entire equation in kilowatt. Then I will convert into megawatt. So look at here. W dot champa. W dot CV is equal to m dot 1 by 2000 in bracket CO square minus CI square plus small ho minus small hi. I think minus is also there. Yes, minus is also there. So let me write minus also. Let me write minus also. W dot CV is equal to minus m dot. So minus m dot is 10 kg per second, 1 by 2000 CO square minus CI square. The data of CO is 80 meter per second. The data of CI is 8 meter per second. 80 square minus 8 square plus what is the data of small ho? Of course, I need to write in kilojoule per kg because I am writing the entire equation in kilowatt. Small ho is 2458.6. 2458.6 minus small hi. What is the value of small hi given in the question? 3018.5. 3018.5. Now, can you tell me what are we getting in kilowatt? After solving, what is the value of W dot CV we are getting in kilowatt? Come on, everyone. 5567. Vineet, very good. 5567.32. 5567.32 kilowatt. And if I'm converting to megawatt, because he's asking in megawatt, 5.5632 megawatt. Oh my God, this is the beautiful answer. 5.5632 megawatt. So he's asking up to 2 decimal place. Let us suppose. Acha, ye to, this is MCQ, na? This is MCQ. This is MCQ. So which option is correct? I think answer is option A. Are you enjoying the jam questions? Are you enjoying? Yes, Navya, very good. Rudra, very good. Lakshmi, excellent. Rohan, beauty. Excellent. I'm telling you, solve each and every question along with me. Yes. Now, the most, again, another most important topic, steady flow energy equation and its application for mixing chamber. Look at here, GATE 2023. I'm making this announcement. In GATE 2023, either in mechanical or XE, you are going to have the question either from nozzle, turbine or mixing chamber. No one can stop. So let us solve one question on mixing chamber. NAT 1 mark. NAT numerical answer type question 1 mark. A hot water stream at 80 degrees Celsius enters steadily into a well insulated mixing chamber with a mass flow rate of 0.5 kg per second. I'm having a well insulated mixing chamber, and what is happening? Hot water stream is entering. The temperature of the hot stream of the water is 80 degrees Celsius and the mass flow rate is given 0.5 kg per second. Now, cold water stream is also entering. Cold water stream enters the mixing chamber at 20 degrees Celsius. So basically, in the mixing chamber, I'm having two inlets. From one of the inlet, I'm having hot water stream entering. From the another inlet, I'm having cold water stream entering. The warm water, which is the mixture of hot water and cold water streams, the warm water stream, which is basically the mixture of hot water stream and cold water stream, leaves the mixing chamber at 42 degrees Celsius. The mass flow rate of a cold water stream is a dash kg per second. Round off to 3 decimal places. Neglect the changes in kinetic energy and potential energy. First of all, let me draw some diagram for this question, then I will be writing the data. Look at here. First I'm drawing the diagram. Look at here. This is your beautiful, yes, this is your beautiful well insulated mixing chamber. This is your beautiful well insulated beautiful well insulated mixing chamber. Now look at here. This is the hot water stream which is entering from this inlet I1. Look at here. Let me say mass flow rate is m dot I1. Of course, this red one is red means hot na re baba. Hot water stream. This is your inlet I1. Hot water stream is entering from this inlet I1. Mass flow rate is m dot I1, and let me say temperature is Ti1. I'm having another inlet from where cold water stream is entering. Let me say inlet I2. From here cold water stream is entering. Of course, let me say mass flow rate is m dot I2, temperature is Ti2. In this insulated mixing chamber, look at here. With this red dotted line, I am representing the control surface, and whatever the region I am having in space which is under observation is my control volume. So this is my control volume. So what is happening inside this well insulated mixing chamber? Hot water stream and cold water stream is getting mixed, and finally the warm water stream is leaving the mixing chamber. That's how Champu is taking the bath nowadays. He is mixing hot water and cold water. Finally, warm water is coming out of the tap, and Champu is happily bathing. Jam bath of Champu. So let me represent outlet by O. So mass flow rate at the outlet is m dot O. Let me say temperature is a TO. Now look at here. What is the data given? A hot water stream at 80 degrees Celsius. Ti1 is given 80 degrees Celsius. Enters steadily into well insulated mixing chamber with a mass flow rate of 0.5 kg per second. M dot I1 is given a 0.5 kg per second. Very good. Cold water stream enters the mixing chamber at 20 degrees Celsius. So Ti2 is given 20 degrees Celsius, the temperature of cold water stream. The warm water stream, which is the mixture of hot water and cold water streams, leaves the mixing chamber at 42 degrees Celsius. TO is given. How much is TO? 42 degrees Celsius. Now what he is asking, the mass flow rate of cold water stream, m dot I2 he is asking in kg per second. But in the question clearly he is saying, steady flow. The moment he is saying steady flow, you have to understand the two things. The first thing, you can write mass flow rate at the inlet is equal to mass flow rate at the outlet. The second thing, you can write a steady flow energy equation, which is basically the conservation of energy for the open system. है ना? चलो, now how to solve this? How to solve this? How to solve this? Can I say I have to apply the steady flow energy equation? Yes. In order to find m dot I2, I will be applying the steady flow energy equation. Look at here. According to SFEE, according to steady flow energy equation. But can I say Q dot is equal to W dot CV plus delta KE dot plus delta PE dot plus delta capital S dot. Out of these 5 terms, if I want to write right now, very good Sanjay, excellent Rohit, I am very happy. Kalpesh, very good. Rudra, excellent. Tarun, very good beta. Look at here. For the time being, what are the things I can write? 0. Look, there is no control volume work. W dot CV is a sunya, है ना? W dot CV is sunya. Well insulated mixing chamber, this is sunya. Neglecting the changes in kinetic energy and potential energy, this is sunya. So basically what I'm getting delta capital S dot is equal to sunya. Now, how to write delta capital S dot? It is basically enthalpy rate at the outlet minus enthalpy rate at the inlet. I am having 2 inlets, no problem. Enthalpy rate at the outlet minus, in bracket, enthalpy rate at the inlet I1 plus enthalpy rate at the inlet I2 is equal to sunya. Now, here comes the most important thing. How to write the enthalpy rate at the outlet? Anyone in the class, beta? Anyone in the class can tell me what will be the enthalpy rate at the outlet? Look at here, mass flow rate at the outlet, I know. Temperature means, look at here, mass flow rate I have written m dot O, temperature I have written TO at the outlet. So can I say, if I want to write m dot O, let me write on next page better. Can I write S dot O is m dot O, T of water, TO, yes, this is the enthalpy rate at the outlet, minus enthalpy rate at the inlet I1, mass flow rate at the inlet I1, which is basically the mass flow rate of the hot water stream, T of water, T I1 plus m dot I2, CW, T I2 is equal to 0. Now CW will be coming common, 0 by CW will be sunya. Alright, shampoo, 0 by CW will be 0 only. So what I'm getting m dot O, TO minus here m dot I1, T I1 plus m dot I2, T I2 is equal to sunya. Look at here, m dot I1 is known, Ti1 is known, Ti2 is known, To is known, m dot I2 I want to find. M dot O, what will be m dot O? Anyone in the class can tell me what I'm going to write in place of m dot O. Arey Champu, the flow is the steady flow. If the flow is a steady flow, mass flow rate at the inlet is equal to mass flow rate at the outlet. What is the mass flow rate at the inlet? M dot I1 plus m dot I2. What is the mass flow rate at the outlet? M dot O. So basically m dot O will be equal to what? M dot I1 plus m dot I2. I will be applying the conservation of mass according to conservation of mass, according to conservation of mass for a steady flow. For a steady flow, what can I write? For a steady flow, I can write, for a steady flow, I can write mass flow rate coming in is equal to mass flow rate going out. M dot I1 plus M dot I2 is equal to M dot O. So let me substitute M dot O over here. Then I will be getting M dot I1 plus M dot I2 here TO minus in bracket what I'm having M dot I1 TI1 plus M dot each and every step I'm writing so that you are able to understand everything, right? Now just substitute the values. M dot I1 is how much beta? 0.5 plus M dot I2 TO is given. Acha, now look at here. Since it is a delta capital H dot is equal to Shunya, I'm having the difference of rate of enthalpy. So you write temperatures in degrees Celsius or Kelvin, doesn't matter, you will be getting the same answer, because look at here, if you are converting into Kelvin, here you will be adding 273, here you will be adding 273, here you will be adding 273. So 273 M dot I1 plus M dot I2, 273 M dot I1, 273 M dot I2, all those things will be getting cancelled. So ultimately whatever you are having in degrees Celsius, that will be remaining. So TO is how much? TO is 42 degrees Celsius minus M dot I1 0.5 into 80 plus M dot I2 TI2 is at 20 degrees Celsius equal to Shunya. Now can you tell me what is the answer you people are getting from here? Anyone in the class can tell me what is the answer you people are getting from here? Quickly. 21 plus 42 M dot I2 minus 40 minus 20 M dot I2 is equal to Shunya. So what I'm getting from here, M dot I2 is equal to 40 minus 21, 19. 42 minus 20, 22. 19 by 22. What is the 19 by 22? Just calculate and tell me what is the answer you people are getting. This is a 0.8636. 0.8636. Beauty, beauty, beauty. What a beauty. What a beauty, what a beauty, what a beauty. 0.8636. 0.8636. So he is asking round off to 3 decimal place. So I will be giving the answer 0.864 and the range is 0.834 to 0.894. Are you able to solve this question? Are you able to solve this question? Come on everyone, come on everyone. Are you able to solve this question? Bolo re baba. Come on, type in chat box. Yes, yes, Taruni, very good. Raghu, excellent, excellent, excellent. Very good, beta. Ganga Rao, excellent. Kusal, beautiful. Now, shall we go for the next? Arun, very good. Shall we go for the next question? Khepe, Khalpes. Yes, Sanjay, very good. Maja, 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 maja. What a beauty! Chalo, chalo, chalo. Let us move forward. Let us move forward. Now the next important topic. Next, yes, 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 yes. Combination of a heat engine and refrigerator. Maybe in place of refrigerator, they can have heat pump also. Maybe in place of refrigerator, they can have heat pump also. But yes, it is again the important topic. It is again the important topic where you are having a combination of a power producing device and a power consuming device. Most important topic. Let us solve one question on this topic. 2 marks. NAT, numerical answer type question. 2 marks. Let me see how many of you will be able to solve this question. Let me see how many of you will be able to solve this question. A reversible heat engine operates between 2 reservoirs at 600 degrees Celsius and 40 degrees Celsius. Okay. I'm having a reversible heat engine which is operating between two thermal two reservoirs, 600 degrees Celsius and 40 degrees Celsius. You must be able to understand this is your source and this is your sink. The heat engine, of course, which is the reversible heat engine, drives our reversible evaporator. The heat engine is driving a reversible evaporator which operates between the same 40 degrees Celsius reservoir and a reservoir at 18 degrees Celsius. Oh my God. Here I want to ask you one question. The reversible refrigerator is operating between two thermal energy reservoirs. One is at 40 degrees Celsius, another is at minus 18 degrees Celsius. Any intelligent student of the class can tell me to which thermal energy reservoir this refrigerator will be rejecting the heat. Anyone in the class can tell me to which thermal energy reservoir this reversible refrigerator will be rejecting the heat. To this reservoir which is at 40 degrees Celsius or this reservoir which is at minus 18 degrees Celsius. That's why I'm asking this question. Listen carefully. To which thermal energy reservoir this refrigerator will be rejecting the heat? What is the aim? What is the aim of refrigerator? You people forget Gajini. The aim of refrigerator to maintain the lower temperature body. How it is maintaining the lower temperature body? By extracting the heat. So what this refrigerator will be doing? It will be extracting the heat from this thermal energy reservoir which is at minus 18 degrees Celsius, and it will be rejecting the heat to this thermal energy reservoir which is at 40 degrees Celsius. I hope everyone is crystal clear, beta. Okay. Now, the heat transfer to the heat engine is 2100 kilojoule. Oh my God. Look at here. The beautiful thing. The net work output of combined plant, reversible heat engine plus reversible refrigerator is 370 kilojoule. The ratio of total heat rejected to the reservoir at 40 degrees Celsius to the heat rejected by the refrigerator to the reservoir at 40 degrees Celsius is a dash. Round off to 2 decimal places. First of all, I'm going to draw the schematic diagram so that you can understand each and everything. Look at here. Let me try to draw the schematic diagram so that you can understand each and everything. I'm having a reversible heat engine which is operating between these two thermal energy reservoirs. pH is equal to constant. Tm is equal to constant. Tm, I have written Tm. Please observe carefully. I'm having a reversible heat engine. Which is operating between these two thermal energy reservoirs. TH is equal to constant and Tm is equal to constant. Of course, reversible heat engine is going to take the heat from TH is equal to constant thermal energy reservoir. Let me say it is a QH. Let me say this is a QH. Fine. Of course, some part of the heat which is getting supplied to reversible heat engine will be getting converted into work. Let me say the net work output of the reversible heat engine is capital W1. And remaining part will be getting rejected to this thermal energy reservoir which is at temperature Tm is equal to constant. So let me say this is QM1. Now what is happening? There is one reversible refrigerator. Look at here, there is one reversible evaporator. This is our reversible evaporator. This is our reversible evaporator. Now, please understand, this reversible evaporator is operating between two thermal energy reservoirs. One is at a Tm is equal to constant, another is at PL is equal to constant. So, what is happening? Try to understand. This reversible evaporator is extracting the heat from here. Let me say QL is the heat extracted. Of course, there will be some work input to this reversible evaporator. Let me say W2 is the work input given to the reversible evaporator, and of course, this reversible evaporator is going to reject the heat to this Tm is equal to constant thermal energy reservoir, which is, let me say, QM2. Now, let me write the data carefully which is given in the question. A reversible heat engine operates between two reservoirs at 600 degrees Celsius and 40 degrees Celsius. 600 degrees Celsius and 40 degrees Celsius. So, TH is given 600 degrees Celsius, which means 873 Kelvin. TM is given 40 degrees Celsius, which means 313 Kelvin. Now, the heat engine drives a reversible evaporator which operates between the same 40 degrees Celsius reservoir and the reservoir at minus 18 degrees Celsius. Yeah, TL is given minus 18 degrees Celsius. Once you tell me, if I am adding 273, how much I am going to get, beta? Just add 273 and let me know. Can I say 255 Kelvin? 255 Kelvin TL. Beautiful. Now, the heat transferred to the engine is 2100 kilojoule. QH is given. QH is how much? 2100 kilojoule. Now, the net work output of combined plant is 370 kilojoule. What is this 370 kilojoule? What is this 370 kilojoule? Anyone in the class can tell me what this 370 kilojoule is given? Jaldi se batao beta. Come on, tell me. What is this 370 kilojoule? This is the most important thing which you have to understand. Look at here. Your reversible heat engine is producing W1 work. Out of this W1 work, we are using W2 to drive the reversible evaporator. So, can you tell me what is the net work output of the system, combined system? Can I say the net work output of the combined system will be W1 minus W2? Come on everyone, tell me this part. Are you able to understand? The net work output will be W1 minus W2. I hope each and everyone is able to understand. Yes, Subarao. Very good, Sanjay. Yes. W1 minus W2 is given in the question, which is basically 370 kilojoule. Now, the ratio of this is the heart of this question. You have to understand what he is asking. The ratio of the total heat rejected to the reservoir at 40 degrees Celsius to the heat rejected by the evaporator to the reservoir at 40 degrees Celsius is. Can you tell me what he is asking in the question? Can you tell me what he is asking in the question? What is the total heat rejected to the 40 degrees Celsius thermal energy reservoir? QM1 plus QM2. QM1 plus QM2. This is the total heat rejected to the 40 degrees Celsius thermal energy reservoir divided by the heat rejected by the evaporator. What is the heat rejected by the evaporator? QM2. This is what he is asking. So, my friends, in order to solve this question, I hope you are able to understand. We have to find QM1, we have to find QM2, then we have to do QM1 plus QM2 divided by QM2, and you will be getting the answer. So, let us work on this QM1. How to find QM1? Yeah, just tell me, Manoj, Just tell me beta, QM1. This is a reversible heat engine. I'm having a reversible cyclic device. And if I'm having a reversible cyclic device, can I apply the thermodynamic Kelvin scale? QH by TH is equal to QM1 by TM. That's it. From here, I will be getting QM1. Yes, beautiful, beautiful. Look at here. I can write according to thermodynamic. Arey baba, if you are solving by the help of thermal efficiency formula, you will be getting the answer. But I know this is a reversible heat engine, so I can apply thermodynamic Kelvin scale according to thermodynamic Kelvin scale. What I'm getting? I'm getting QH by TH. QH by TH is equal to QM1 by TM is equal to W1, which is the work output of the reversible heat engine, by TH minus TM. Now, first I will be finding QM1. So what is a QM1? QM1 will be TM by TH into QH. So what is the QM1 I'm getting beta? What is the QM1 I'm getting? TM by TH. TM by TH 313 by 873 into 2100 kilojoule. Beta jaldi se, come on everyone, tell me quickly, what is the value of QM1 you people are getting? QM1, I want Chaudhary, very good beta. 752.92. 752.92 kilojoule. This is my QM1. Now I want to find QM2. Yaar, look at here. This device is also, Champa, look at here. This device is also reversible cyclic device na. Reversible is also reversible cyclic. I can apply the thermodynamic Kelvin scale here also. Champu, if you are using COP formula, no problem, you'll be getting the answer. But I am solving in the smarter way. Let us again apply the thermodynamic Kelvin scale for reversible refrigerator. Look at here. According to thermodynamic, Kelvin scale, again I'm writing for reversible refrigerator. What is going to come? Look at here. QM2 by TM is equal to QL by TL is equal to W2 divided by TM minus TL. So QM2 by TM is equal to QL by TL is equal to W2 divided by TM minus TL. Look at here, I want to find QM2. If I take first term and last term, so can I write TM by TM minus TL into W2? Now the thing is, if you want to find QM2, TM you know, TL you know, W2 you have to calculate. Anyone in the class can tell me, if I want to calculate W2, what I need to calculate? Tell me better quickly. If I want to find W2, what I need to calculate? Look at here in the question, he has given me W1 minus a W2. In the question, he has given the net work output of the system of the plant. W1 minus W2, 370 kilojoule. So if I want to find W2, first I need to calculate W1. Again, can I calculate W1 from here? QH I know, TH I know. TH minus TM I know. W1 will be getting calculated from here. So what is the value of W1 I'm going to get? W1 is equal to और a jam question है बाबा, TH minus TM by TH into QH. So W1 is equal to TH is how much? TH is 873 Kelvin minus 313 Kelvin divided by TH is how much beta? 873 Kelvin into 2100. Anyways, there is another way also. You already know QH. You already know QM1. You can subtract both of them. You will be getting W1. W1 you can calculate from there also. No problem at all. Anyways, what is the value of W1 you are getting? Anyone in the class can tell me what is the value of W1 you people are getting from here? W1, come on everyone. 1347.08. 1347.08 kilojoule. But please cross check. Please cross check once. Is it same as, mathematically it must be same as QH minus QM1. If you are subtracting 752.92 from 2100, you must get the same, because if you see reversible heat engine, you know the value of QH, you have calculated QM1. So net work output of this reversible heat engine, or you can say the work output of this reversible heat engine, it must be QH minus QM1. So you can calculate in this way also. So W1 you got. Once you got W1, W2 is basically, look at here, how to find the W2? Yo, champa. W1 minus W2. W1 minus W2 is given in the question, which is basically 370 kilojoule. So from here, you can easily calculate W2. So what is a W2 beta? W1 minus 370. 1347.08 minus 370. So what is a W2 you people are getting in kilojoule? Anyone in the class can tell me what is the value of W2 we are getting beta? 977.08. Yes, very good. 977.08 kilojoule. This is the value of W2. Once you got W2, you can easily calculate QM2. TM, how much is a TM? 313 Kelvin divided by TM minus TL, 313 Kelvin minus a TL. TL is how much? 255 Kelvin into W2, 977.08. Oh my God. Oh my God. Can you tell me what is the value of QMP? You people are getting. Come on everyone. What is the value of QMP? You people are getting. QM2 313 divided by 313 minus 255. And 977.08 5272.86 kilojoule. This is QM2. Now what he is asking in the question beta? What he is asking in the question? He is asking in the question, I hope you are able to understand. Look at here, QM kya? What is this QM1? What is this QM1? This QM1 is the heat rejected by the reversible heat engine to TM thermal energy reservoir, which is at 40 degrees Celsius. This is the QM1. The heat rejected by reversible heat engine to the thermal energy reservoir, which is at 40 degrees Celsius. What is this? The QM2 which I calculated just now. It is the heat rejected by the reversible reflector to this thermal energy reservoir, which is at 40 degrees Celsius, 313 Kelvin. So in the question, he is asking QM1 plus QM2 divided by QM2. So what I'm going to get, what is the QM1? 752.92. What is the QM2? 5272.86 divided by QM2. QM1 plus QM2 divided by QM2. How much I'm getting? How much I'm getting? Come on, everyone. 1 point. Very good, Lakshmi. Bhavya, very good. 1 point. Yes. 1.1428. This is the answer. This is the answer. 1.1428. 1.1428. Round off to 2 decimal place. So 1.14. How many of you got this answer 1.14? How many of you got this answer 1.14? The range for this question is 1.12 to 1.16. This is the range. 1.12 to 1.16. Beauty, beauty, beauty. Gangarao, excellent. Saurabh, beauty. Yes. Yes, Majhe, Govinda, excellent. Mayank, Kusal, Aage Garo, beauty, beauty, beauty. Habib, very good. Yes, Aditya, excellent. Amit, very good, beta. Now, let me frame one bacha question out of this data. Let me frame one bacha question out of this data. Let us suppose he is asking one question in this way. What is the ratio of work output of the reversible heat engine to the, listen carefully re baba champo, let me frame one bacha question from here. What will be the ratio of work output of the heat of the reversible heat engine to the work input to the reversible refrigerator? First of all, see the diagram and tell me what he is asking in the question. What is the ratio of work output of the reversible heat engine to the work input to the reversible refrigerator? What he is asking in the question. First of all, you tell me this part. What he is asking in the question. What is getting asked in the question? Can you tell me? He is asking W1 by W2. First of all, you tell me W1 by W2 will be greater than 1 or less than 1. It has to be greater than 1, because what is happening, whatever the output I am getting from the reversible heat engine, some part is getting supplied to the reversible refrigerator to operate it, and yes, remaining is the net work output of the power plant, of the combined plant. Not the power plant, of the combined plant. So 100% W1 is greater than W2. He is asking W1 by W2. If W1 is greater than W2, W1 by W2 has to be greater than 1. Your answer must be greater than 1. So yes, you have calculated W1. You have calculated W2 and you will be getting the answer. Now, the next. Are you enjoying? Are you enjoying? Are you getting the feel of the questions? Each and every question is a brand new question which will be giving you the different perspective of the concept. Now, the next important topic. The next important topic is a Clausius inequality. Next important topic is a Clausius inequality. For a cycle, cyclic integral del Q by T will be always less than equal to 0. If the cycle is internally reversible cycle, equal symbol will come. If the cycle is internally irreversible cycle, less than will come. Let us solve one question. But this is extraordinary question, MSQ. Solve it very, very, very carefully. Solve it very, very, very carefully. MSQ 2 marks. MSQ 2 marks. A reversible heat engine. The moment in the question he has given reversible heat engine, you have to understand I am having internally reversible cycle as well as externally reversible cycle, because reversible heat engine will be operating on reversible cycle. A reversible heat engine receives heat from two thermal energy reservoirs. Oh my God! It is receiving the heat from two thermal energy reservoirs maintained at constant temperature of 750 Kelvin and 500 Kelvin. Okay. The engine develops a work output of 100 kilojoule and rejects 60 kilojoule of heat to a thermal energy reservoir at a constant temperature of 250 Kelvin. Which one or more of the following statements are correct? First of all, whenever in the question you are having more than one source or more than one sink, you have to understand, you have to apply the Clausius inequality. How many sources I am having in this question? In this question I am having two sources. One is at 750 Kelvin, another is at 500 Kelvin. So 100% I will be using the Clausius inequality to give the answer of this question. First of all, let me try to draw the schematic diagram so that you can understand each and everything in a proper way. Look at here. Look at here. This is your reversible heat engine. This is your reversible heat engine. Yes, this is your beautiful reversible heat engine. Now, this reversible heat engine is getting the heat from two sources. Let me say this is one of the source which is supplying the heat to this reversible heat engine, and this is another source which is supplying the heat to this reversible heat engine. Let me say this source is at temperature T1 is equal to constant and supplying the heat QH. Q1, let me say this is the source which is at temperature T2, and let me say it is supplying the heat Q2. What a beauty, what a beauty, what a beauty. Now, there is a sink. There is a sink. There is a sink. Let me say this is the sink which is at a temperature T3 is equal to constant. This is the sink which is at temperature T3 is equal to constant, and let me say the heat rejected to this sink is Q3, and yes, this reversible heat engine is going to produce some work output. Let me say that is capital W. Now, whatever the data given in the question, whatever the data is given in the question, let me write it carefully. Whatever the data is given in the question, first of all, let me write it carefully. T1, a reversible heat engine receives heat from two thermal energy reservoirs maintained at constant temperature of 750 Kelvin and 500 Kelvin. So basically T1 is given 750 Kelvin and T2 is given 500 Kelvin. Beautiful. Now, the engine develops a work output of 100 kilojoule. Work output of 100 kilojoule. That means W is given. W is how much? 100 kilojoule. Okay. And rejects 60 kilojoule of heat to a thermal energy reservoir at constant temperature of 250 Kelvin. So heat rejected Q3 is given 60 kilojoule. And yes, temperature of the sink is given 250 Kelvin. Okay. Now, in statement A, he is talking about thermal efficiency of heat engine. In statement B, he is talking about thermal efficiency of heat engine. So, statement A, statement B, he is talking about thermal efficiency only. What he is saying in statement C, heat supplied by the thermal energy reservoir at 500 Kelvin is statement D में heat supplied by the thermal energy Roshan Kumar. In C and D, he is asking the same thing. How C and D both can be correct? Either C will be correct or D will be correct. In C or D. Or Champu. Either C will be correct or D will be correct or both will be wrong. But both of them can never be correct. Heat supplied by the thermal energy reservoir at 500 Kelvin is. Heat supplied by the thermal energy reservoir at 500 Kelvin is. Okay, let us solve. Thermal efficiency. Beta, what is the basic formula of thermal efficiency? What is the basic formula of thermal efficiency, beta? What is the basic formula of thermal efficiency? You have any power producing cycle, the basic formula is saying net work divided by heat supplied. In this case of reversible heat engine, network I am representing by W. Heat supplied is what? Heat supplied is Q1 plus Q2. I have to find W by Q1 plus Q2. W I know. Very good, Manisha. Very good, beta Manish. Puspa, very good. W I know. Can I calculate somehow this Q1 plus Q2? Yes, I can calculate Q1 plus Q2. I am having reversible heat engine. This reversible heat engine is the cyclic device, and I know according to first law of thermodynamics. According to first law of thermodynamics, what can I write? Net heat interaction is equal to net work interaction. What is the net heat interaction? Q1 plus Q2 minus Q3. Why I'm writing minus with Q3? Because Q3 is the heat rejected, is equal to network output. What is the network output? Capital W. So from here I can easily find Q1 plus Q2. From here I can easily find Q1 plus Q2. Q1 plus Q2 is equal to W plus Q3. So Q1 plus Q2 is equal to W is 100 kilojoule, Q3 is 60 kilojoule. So Q1 plus Q2 is equal to how much, beta? 160 kilojoule. The moment I am getting Q1 plus Q2, thermal efficiency I can calculate W, which is 100 kilojoule, divided by Q1 plus Q2, which is 160 kilojoule, and this will be how much? 0 is getting swaha. 5 by 8. 8 6 ayayo. 8 6 ja 48. 0.625 percentage. In percentage is asking. But can I say 62.5%? First you confirm me this part. Can I say thermal efficiency of this reversible heat engine is 62.5%? Yes, very good, Chaudhary. Yes, Roshan, excellent. Beauty. 62.5% is the thermal efficiency. So yes, statement A is correct, statement B is wrong. Now he is asking what? Heat supplied by the thermal energy reservoir at 500 Kelvin. Tell me, he is asking Q1 or Q2? If T1 is 750 Kelvin, Subbarao, very good, beta. If T1 is 750 Kelvin, T2 is 500 Kelvin, tell me clearly whether he is asking Q1 or Q2. Heat supplied by the thermal energy reservoir at 500 Kelvin. Which thermal energy reservoir is at 500 Kelvin? This is at 500 Kelvin. So he is asking Q2. He is asking what is the value of Q2. No, Q2 is asking, Ray Baba. So look at here. Acha, how to find Q2? Anyone is getting some idea? How to solve for Q2? I will be applying the Clausius inequality. That equal part I am going to write according to Clausius inequality. What I am having? Cyclic integral del Q by T is less than equal to 0. Of course, in this case, I am having internally reversible cycle. So equal to part will come. So equal to part will come. So what I'm going to get? Cyclic integral del Q by T is equal to 0. And since I'm having a reversible heat engine, and this reversible heat engine is externally reversible cycle also, I'm going to write this cyclic integral del Q by T as Q1 by T1 plus Q2 by T2 minus Q3 by T3. Sir, why minus? Because Q3 is the heat rejected. So what I'm going to get? Q1 by T1 plus Q2 by T2 minus Q3 by T3 is equal to Shunya. Why I'm able to write like this? I'm able to write like this because my cycle is externally reversible cycle also. Now, please listen. I need to find the Q2. So Q1 can be written as, look at here, Q1 plus Q2 is 160 kilojoule. So from here, what is the Q1? I want to write Q1 in terms of Q2, 160 minus Q2, na? So what I'm going to get? 160 minus Q2 divided by T1. In place of Q1, I have written 160 minus Q2 plus Q2 by T2 minus Q3 by T3. Q3 by T3 is equal to Shunya. 160 minus Q2. T1 is 750 Kelvin. Q2 by 500 minus 60 by 250 Kelvin is equal to 0. LCM. Let me say LCM is coming 1500. I'm taking 1500. So here it will be getting multiplied by 2, 320 minus 2 Q2. Here it will be getting multiplied by 3 Q3. Here it will be getting multiplied by 6, 360. Yeah, tell me how much you are getting. 1500 in 0 is 1500 in 0 is 0. So yeah, Q2 is, according to me, here it is Q2, na? 1 minute, Champa. Q2 minus 40 is equal to 0. Yeah, Q2 according to me is coming 40 kilojoule. You tell me, is it correct? Is it correct? Q2 is 40 kilojoule. Is it correct? And if a Q2 is a 40 kilojoule, then which answer is correct? Yes. Which statement is correct? Statement C is correct. Statement D is wrong. Now, listen carefully. I'm changing one small thing and then you have to tell me. Let us suppose here in place of 500 Kelvin, I am writing 750 Kelvin. Now you tell me which statement will be correct. If in place of 500 Kelvin, I am writing 750 Kelvin, then which statement will be correct? Look at here, the moment I am saying what is the heat supplied by the thermal energy reservoir at 750 Kelvin, that means I am asking Q1, and if I am asking Q1, you have calculated Q2 which is coming 40 kilojoule, and you know Q1 plus Q2 is equal to 160 kilojoule, Q1 will be 120 kilojoule, and then the answer will be statement D, which is a correct, not statement C. Right. So for this question, answer is A, C. Are you enjoying the jam questions? Are you enjoying the jam questions? Bol rahe ho, but type in chat box. Are you getting the solutions maybe by yourself or along with me? The entire chat box must be red. Ho jaye re baba. What a beauty. Come on everyone. Yes. Let's go to the next question. Maja, 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 maja. Now, the next most important topic, the next most important topic from where you can expect the question is calculation of entropy change for various processes executed by the perfect gas. They will be giving you the perfect gas and they will be asking you calculate the entropy change of perfect gas, and I'm telling you this is a very important topic. Calculation of entropy change in various processes executed by the perfect gas. If you see the previous gate questions, you'll be seeing number of questions has been asked on this particular topic. Let us take one question. NAT. Let us take one question. NAT, numerical answer type question. There is a space, you have to fill the space, and this question is of 1 mark. Of course, you are solving the questions along with me, so I'm not going to give you that straightforward question which comes in gate examination. I have twisted this question a little bit. A piston cylinder arrangement contains argon gas. Look how kind-hearted this person is. He has given the molar mass of argon also. You should remember, look, hydrogen, nitrogen, helium, argon. You should remember oxygen, carbon dioxide. You should remember, you should know the molar mass. If it is not given in the question, you cannot say, sir, the molar mass was not given, so I will challenge this question, I will contest this. They will kill you. Molar mass of argon is given 40 kg per kilomole. The gas undergoes a compression process from state 1. What is the state 1? 500 Kelvin, 2 meter cube to state 2. 400 Kelvin. Oh my God. If the change in specific entropy of the argon during the process is minus 0.3 kilojoule per kg per Kelvin, then the final volume of the argon gas is a dash meter cube. Assume argon is behaving as perfect gas. Anyone in the class can tell me? Final volume V2 can be what? Any random guess you can make. About V2. What will be V2? What can be the value of V2? Read, look, that's what I'm saying. You have to develop that instinct that just after reading the question, something will come in your mind. Okay, this can be the answer. Look at here. I'm having the compression process. What is the meaning of compression process? The meaning of compression process, volume is going to decrease. So if initial volume is a 2 meter cube, the final volume has to be less than 2 meter cube. If anyone is getting the answer 4.5 meter cube, I will kill you. You cannot have the volume more than 2 meter cube because it is the compression process. Yes, Sarah, very good. Now let us solve. First, let me write the data for you. Look, he has given you the argon gas. Argon gas is a monoatomic gas or diatomic gas or triatomic gas? If you don't know this, you cannot solve this question. Argon is monoatomic gas. Argon is monoatomic gas. AR you are writing, na champa. Molar mass of argon is given 40 kg per kilomole. Molar mass of argon is given 40 kg per kilomole. The gas undergoes a compression process from state 1. At state 1, temperature is given 500 Kelvin. The volume is given 2 meter cube. To state 2, at state 2, temperature is given T2 and it is given as 400 Kelvin. Now, if the change in specific entropy of argon during the process is minus 0.3 kilojoule per kg per Kelvin, delta small s, specific entropy change is given minus 0.3 kilojoule per kg per Kelvin. Then the final volume of the argon gas is capital V2 he is asking, in a meter cube. Yeah, of course, you have to apply the formula of specific entropy change of perfect gas. But which formula? You have to apply that formula where you are having T2 by T1, where you are having V2 by V1. You have to apply that formula where you are having T2 by T1, where you are having V2 by V1. So delta small S1 to 2. Look at here. T2 by T1. V2 by V1, ln, here I am having T2 by T1, here I am having V2 by V1, so you are able to recollect. If you are having V2 by V1 over here, CV will come. If you are having T2 by T1 here, so R will come. अब देखो, now please listen. Delta small s1 to 2 is given, T2 is given, T1 is given, V1 is given, V2 we need to find. Of course, small V2 by shampoo. Look at here. Don't be confused. Look at here. In actual formula, you are having a small V2 by small V1 ratio of specific volumes, but you know, small V2 by small V1 is basically the ratio of total volumes only, because mass is constant. Anyways, the question is, I don't know CV, I don't know capital R. Can you tell me how can we calculate CV and capital R? Look at here, beta. This is the beauty of this question. First, I will be calculating capital R. How to find capital R? Universal gas constant divided by molar mass. So characteristic gas constant is 8.314 kilojoule per kilomole per Kelvin divided by 40. So what is the characteristic gas constant you are getting? 8.314 divided by 40. 0.20785 kilojoule per kg per Kelvin. Yeah, please confirm me this part. Are you getting capital R? Same. Very good, Rudra. Yes, this is capital R. Now I need to find the CV. What will be CV? Capital R upon gamma minus 1. Capital R I have calculated. Now here, what is the value of gamma I am going to substitute? Anyone in the class can tell me what is the value of gamma we are going to substitute over here? Yes, monoatomic gas. For monoatomic gas, gamma is 1.667. Tell me, what is the value of CV we are getting from here? 0.311, 0.31162 kilojoule per kg per Kelvin. The moment you got CV and capital R, now there is nothing in the question. Just substitute the values. You will be getting the answer. Delta small s1 to 2 is given minus 0.3. CV is 0.31162 ln T2 by T1. 400 by 500 plus capital R 0.20785 ln V2 by V1. V1 is given in the question. What is V1? 2 meter cube. Now you need to solve this. You will be getting the answer minus 0.3. What is this value, beta? What is this value? 0.31162 ln 400 by 500. Of course, it will be negative because inside the ln you are having less than 1. Minus 0.0695 plus 0.20785 ln V2 by 2. So 0.20785 ln V2 by 2 Look at here, this will be going here and it will become positive. So how much I am getting? Minus 0.2305. है ना? So from here, if I want to write, V2 will be 2 times of e to power ln will become e minus 0.2305 divided by this will be coming into division 0.20785. Anyone in the class can tell me after solving this how much you are getting? Of course you are getting less than 2 because e to power minus you are having. If you are having e to power minus, tell me how much you are getting. 0.6598. Yes, very good. 0.6598 meter cube. This is the final volume. 0.6598 meter cube. 0.6598 meter cube. Round off to 2 decimal places. 0.66. 0.66. The range for this question is 0.64 to 0.68. How many of you are getting this? How many of you are getting this? What are you? Yes. Are you people happy? Means I hope you people are happy that we are solving the questions in a jham way. Is there anyone who is able to solve all the questions whatever we have discussed till now? Is there anyone in the class attending who have solved all the questions correctly along with me? Very good, Rahul. Are maja. Mayank, Rohit, Habib, Himanshu, Rudra, Rohan, Lakshmi, Mayank, Kshitij. Wah, what a beauty. Sukumar, very good. Majhe, Lucky, excellent beta. Very good, Sanjay, excellent. The next important topic. In the last topic, we have calculated the entropy change of perfect gas. At the same time, you should know how to calculate the entropy change of incompressible substance. How to calculate the entropy change of incompressible substance in general whose specific heats are constant. Now, NAT, numerical answer type question, 2 marks. Of course, water will be getting treated as incompressible substance having constant specific heat. 1 kg of water is heated from 280 Kelvin to 350 Kelvin by first bringing it into contact with a reservoir at 310 Kelvin, where it is getting heated from 280 Kelvin to 310 Kelvin, and then with a reservoir at 350 Kelvin, where it is getting heated from 310 Kelvin to 350 Kelvin. The entropy change of the universe is a dash. He is asking in joule per Kelvin, round off to 1 decimal place. CW is equal to 4.18 kilojoule per kg per Kelvin. Try to understand what is given in the question. Look at here. There is a thermal energy reservoir which is of course behaving as source. This is at temperature TH1. Water of mass 1 kg is coming into contact with this thermal energy reservoir, and the temperature of water is increasing from initial temperature T1 to TH1. The moment the temperature reaches to TH1, now this 1 kg of water is coming in contact with another thermal energy reservoir which is at temperature TH2. Now what is happening? this water is getting heated from this temperature TH1 to T2. Of course, this T2 is nothing, TH2 only. Look at here, I will be explaining you the diagram clearly. Let me write the data. 1 kg of water. The mass of water is 1 kg. The mass of water which I am representing by this blue color ink is 1 kg. This is water. Alright, Champo, this is water. This is water whose mass is given as 1 kg. Now, 1 kg of water is heated from 280 Kelvin to 350 Kelvin. Initial temperature of the water is 280 Kelvin. Initial temperature of the water is 280 Kelvin to 350 Kelvin. T2 is 350 Kelvin. By first bringing it into contact with the reservoir at 310 Kelvin. TH1 is given 310 Kelvin. So, when water of mass 1 kg is coming in contact with this thermal energy reservoir which is at 300 Kelvin, what happens? The temperature of water increases from 280 Kelvin to 310 Kelvin. Now, of course, I cannot have the temperature beyond 310 Kelvin because the temperature of the source which is having temperature 300 Kelvin, it cannot increase the temperature of water beyond this. Now what happens? And then with the reservoir at 350 Kelvin, look at here, this is another reservoir which is at 350 Kelvin. The moment temperature of water is increasing to 300 Kelvin, it is brought in contact with this another thermal energy reservoir which is at 350 Kelvin, and the temperature of water increases from 300 Kelvin to 310 Kelvin to 350 Kelvin. T2 is 350 Kelvin. And of course, TH2 is also 350 Kelvin. What he is asking? The entropy change of the universe is, he is asking the entropy change of universe in joule per Kelvin. Let me keep the things very simple. Let me say this water is my system. Let me say this water is my system. I am drawing the boundary like this. So I am trying to tell you is my system is water. If water is my system, what I am having in surrounding, beta? Where I will be seeing the entropy change, what I am having in surrounding, where I am going to see the entropy change. Look at here, if water is my system, then this is in surrounding, this is in surrounding where I will be seeing the entropy change. So can I say in very simple words, look at here, in very simple words, I can write, if I want to find the entropy change of universe will be entropy change of system plus entropy change of surrounding. System means already I have assumed water. Entropy change of water in surrounding where the entropy change will take place, it is my two thermal energy reservoirs. Entropy change of first thermal energy reservoir having temperature TH1, entropy change of second thermal energy reservoir which is having temperature TH2. Can I write like this? Once I am able to write like this, things will become very easy. Are you able to understand this, beta? If he is asking find the entropy change of universe, what I need to do is I need to find the entropy change of water, I need to find the entropy change of this thermal energy reservoir, I need to find the entropy change of this thermal energy reservoir, and the moment I am adding all of them, I will be getting the entropy change of universe. Is it clear to each and everyone? Saurabh, very good. I hope everyone is crystal clear with this. I hope each and everyone is crystal clear with this. Now look at here. First, I will be finding the entropy change of water. Water is behaving as incompressible substance having constant specific heat which is given in the question 4.18 kilojoule per kg per Kelvin. Can I find the entropy change of water? Can I find the entropy change of water? Yes. How to find the entropy change of water? Water is behaving as incompressible substance having constant specific heat. I can write MC ln final temperature of water, which is the T2, divided by initial temperature of water, which is the T1. Of course, temperature of water is increasing, entropy change must be positive because entropy is going to increase. Mass is 1 kg, C is a 4.18 kilojoule per kg per Kelvin. Ln T2 is how much? 350 Kelvin. Final temperature of water is 350 Kelvin. Initial temperature of water is 280 Kelvin. Can you tell me what is the entropy change of water we are getting? What is the entropy change of water we are getting? Come on, everyone. What is the entropy change of water we are going to get? Anyone in the class can tell me what is the entropy change of water we are going to get? 100% it must be positive. 100% it must be positive. 0.93274 kilojoule per Kelvin. So entropy change of water is coming. Entropy change of water, if I convert into joule per Kelvin, 932.74 joule per Kelvin. This is the entropy change of water. This is the entropy change of water. Now, please listen carefully. Please listen carefully. Anyone in the class can tell me what will be the entropy change of thermal energy reservoir 1. What will be the entropy change of this source? It will be positive or negative. It will be positive or negative. Anyone in the class can tell me if I want to find the entropy change of thermal energy reservoir 1, it will be positive or negative. First of all, you should have the look. Calculation number is one thing, the calculation of number is one thing, but to have the rough idea of numbers is the another thing. You are having the water, the temperature of water is increasing, the entropy change must be positive. But what will be the entropy change of this thermal energy reservoir 1? It must be negative. It must be negative. Why it must be negative? Because heat is getting supplied by this thermal energy reservoir 1 to the water. Next question. Anyone in the class can tell me? Anyone in the class can tell me what will be the entropy change of this thermal energy reservoir 2? What will be the entropy change of this thermal energy reservoir 2? Can I say the entropy change of this thermal energy reservoir 2 will also be negative? Now, look at here. You must have the feel of numbers. This is a positive. This is a negative, this is negative. You got this value as 932.74. Now I am having very simple question. This is negative, this is negative. The sum of these two negatives must be more than 932.74 or less than 932.74. Look at here. I will be calculating the value, it will be coming negative. I will be calculating the value, it will be coming negative. My next question to you people is, if I do the addition of these two negatives, it must be less than 932.74 or more. It must be less. Why less? Why less? Why less? Why less? Both will be negative, but why the summation will be less? Because he is asking the entropy change of universe, and I have told you, entropy of universe can never decrease. Entropy change of universe can never be negative. Entropy change of universe will be positive for irreversible process. Entropy change of universe will be 0 for reversible process. Here I am having the irreversible process, so 100% entropy change of universe must be positive. So this number has to be greater than the magnitude of these two numbers. You calculate this, both will be coming negative, and the summation will be less than 932.74. And if you are able to understand, entire chat box must be red. लाल हो जाए रे बाबा. चलो. Now, how to calculate the entropy change of reservoir 1. Now, how much is the heat supply? Of course, it will be negative. Of course, it will be negative. I will be writing like this. Entropy change of thermal energy reservoir 1 is equal to negative. How much is the heat supplied? Mass, C of water. Temperature of water is increasing from T1 to TH1. So TH1 minus a T1 minus MC TH1 minus T1. This is the heat supplied to the water. Of course, negative sign I have written. Entropy is decreasing, divided by constant temperature of the thermal energy reservoir, which is a TH1, which is a TH1. So can I say delta S1 is equal to minus 1 into 4.18 TH1, 310 Kelvin minus 280 divided by TH1, which is how much? 310. So tell me beta, how much you are getting? What is the entropy change of thermal energy? It has to be negative. How much you are getting? In negative, how much you are getting? Minus का 0.40452 kilojoule per Kelvin. If I convert into joule per Kelvin, can I say minus 404.52 joule per Kelvin? Am I getting this number correct? Tell me. Excellent. Beautiful beta. Beautiful. Sanjay, excellent. Now, similarly, I am finding entropy change of reservoir to negative. How much is the heat supplied to water? Mass of water, C of water, T2 minus a TH1. M C of water, T2, funnel temperature is T2 minus a TH1 divided by temperature, constant temperature of thermal energy reservoir 2, which is basically TH2. Let us substitute the values. Minus 1 into 4.18. What is the value of a T2? Funnel temperature 350 Kelvin minus a TH1 310. TH2. TH2 is how much? 350. What is the entropy change of thermal energy reservoir 2 we are getting? Minus ka, of course, minus ka 0.477714 kilojoule per Kelvin. Now, can I write delta S2 is equal to 477.71 joule per Kelvin? Joule per Kelvin. Now, add all the numbers. Add all the numbers in order to get the entropy change of universe. So, entropy change of universe. Entropy change of universe is equal to entropy change of system, entropy change of water, which I got 932.74. 932.74 plus entropy change of reservoir 1, which is coming negative 404.52. 404.52. Of course, entropy change of reservoir 2 is also negative 477.71. Everything is in joule per Kelvin. Can you tell me what is the entropy change of universe you are getting? You can check the summation of these two. If you see the magnitude wise is less than 932.74. How much we are getting, beta? How much we are getting? 50.51. Oh ho ho, beauty! Excellent! Excellent! 50.51 joule per Kelvin. This is the entropy change of universe. This is the entropy change of universe. 50.51. 50.51. What a beautiful question. 50.5 I will be giving you because he is asking round off to 1 decimal place. And the range is beautiful, beta, beautiful. 48.5. Champu nahi banega, board. 52.5. This is the range. Are you able to solve this question? Are you able to solve this question? Come on, everyone, type in chat box. Are you able to solve this beautiful question? Now, I'm bringing one very challenging question to you. I'm bringing one very challenging question to you. The next important topic is entropy balance equation for open system. Entropy balance equation for open system. If you are preparing for XC, I am telling you question is coming from here. If you are preparing for XC, question is coming from here. In mechanical, last year question came from here. Last year also question came from here. So be careful, be careful. Oh my God. This is really a brilliant question. Please solve this question. I'm telling you, you will not have such a beautiful question frequently. MSQ, multiple select question, 2 marks. Multiple select question, 2 marks. Air enters an insulated turbine operating at steady state at 600 kilopascal, 900 Kelvin and exits at 300 kilopascal. What is the data given? I'm having insulated turbine. Air is entering in this insulated turbine, and of course this turbine is operating at steady state. The inlet pressure is 600 kilopascal, inlet temperature is 900 Kelvin, and the pressure at the outlet is a 300 kilopascal. Now, a thermocouple, yes, at the outlet of the turbine, we are having a thermocouple which is giving the reading. A thermocouple indicates that the exit air temperature is approximately 480 Kelvin. There is a thermocouple mounted at the outlet of insulated turbine, and the reading of this thermocouple is showing 480 Kelvin is the temperature of the air at the outlet. Which one or more of the following statements are correct? Neglect kinetic and potential energy effects. Now look at here. What a beautiful question. What a beautiful question. Statement A, exit temperature indicated by thermocouple is correct. Means the thermocouple is saying outlet temperature is 480 Kelvin. This is correct. Statement B, exit temperature indicated by thermocouple is incorrect. Statement C, if air is assumed to undergo isentropic expansion in the turbine, the exit temperature is 735.4 Kelvin to 741.4 Kelvin. If the air is assumed to undergo isentropic expansion in the turbine, the power doubled by turbine is 160 kilojoule per kg to 164.4 kilojoule per kg. What a beautiful question. How are you going to evaluate whether the exit temperature indicated by thermocouple is correct or incorrect? What a beautiful question. What is coming in your mind? What is coming in your mind? Whether the reading of thermocouple is correct or incorrect. Whenever such questions are coming, whether this reading is correct or incorrect, listen carefully. There is one beautiful method by which you can say, calculate the entropy generation. Calculate the entropy generation within the control volume. If the entropy generation within the control volume is a positive, yes, this reading is correct. But if it is coming negative, this reading is incorrect, because entropy generation cannot be negative. Anna? Let me do slight change. The exit temperature in your thermocouple may be correct, may be incorrect. Chalo, whatever the data is given, let us write. Air enters an insulated turbine operating at a steady state at a 600 kilopascal. PI is given. Ti is given 600 kilopascal, right? Ti is given 900 Kelvin. Pressure at the outlet of turbine is known 300 kilopascal. And of course, the reading of turbine outlet temperature given by thermocouple is 480 Kelvin. Now I need to check whether this is correct or incorrect. But how to solve? Look at here. Look at here. Can I say according to Champa, look at here. According to entropy balance equation for open system. This is very, very, very important. According to entropy balance equation, whatever the PDF I'm going to give you today, take the print of that and match with your GATE 2023 mechanical and XC paper. I'm telling you, you'll be finding so many relevant questions from here. According to entropy balance equation for open system. What is that? What is that? Look at here. Rate of change of entropy of the control volume plus delta S dot of the fluid is equal to rate of entropy transfer along with the heat transfer plus rate of entropy generation within the control volume. Now, where out of these four terms, two terms are shunya. Can you tell me which two terms are shunya? Out of these four terms, two terms are shunya. Out of these four terms, two terms are shunya. My turbine is operating under steady state. If my turbine is operating under steady state, ds by dt of the control volume is shunya because my turbine is operating under steady state. I am having well insulated turbine. If I am having well insulated turbine, there is no heat interaction. If there is no heat interaction, entropy transfer along with heat transfer is shunya because I am having well insulated turbine. Now look at here. Can I write in this way? Delta S dot F is equal to rate of entropy generation in control volume. If I'm writing in per unit mass, look at here. Let me write in this way first. Rate of entropy generation in control volume is equal to delta S dot F. And if I write in per unit mass, yes, entropy generation in the control volume per unit mass is equal to delta small s of the fluid. Now, can I find delta small s of the fluid? Yes, I can easily find delta small s of the fluid. I know Pi, I know Ti, I know Po, and yes, To, the reading of the thermocouple is known to me. So I can find, look at here, delta small s G within the control volume is a Cp ln Po by Ti minus R ln Po by Cp 1.005 kilojoule per kg per Kelvin ln To is how much better? 480 Kelvin divided by Ti. Ti is how much? 900 Kelvin minus R 0.287 kilojoule per kg per Kelvin ln Po by Pi. Po is how much? 300 kilopascal by 600 kilopascal. But tell me quickly, what is a small Sg within the control volume you are getting? What is the specific entropy generation within the control volume you are getting? Come on, tell me. Minus ka 0.4328. Is it coming negative? Is it coming negative? If it is coming negative, entropy generation can never be negative. Entropy generation can never be negative. If entropy generation can never be negative, impossible. This is impossible. And if this is impossible, can I say, look at here, exit temperature indicated by thermocouple. Let me be very clear. It's incorrect. It's incorrect. It's incorrect. So A is a wrong statement. B is correct. Are you getting how to check? Are you getting how to check whether it may be correct or it may be incorrect? Now, next part, if air is assumed to undergo isentropic expansion, if air is assumed to undergo isentropic expansion in the turbine, the exit temperature is TO, he is asking. Yeah, now from here onwards, there are two ways to solve this question. Look, if we are having isentropic expansion, you know you can apply this formula. Delta small s of the fluid from inlet to outlet is 0. Isentropic expansion means this, na? This is the meaning of isentropic expansion. But I know after solving this what I'm going to get. Look at here. I hope you are able to recollect. If I am having a perfect gas undergoing isentropic expansion, you know this formula, Tp power 1 minus gamma upon gamma is equal to constant. So you are going to get something like this. Pi power 1 minus gamma upon gamma is equal to PO power 1 minus gamma upon gamma. So you need not to fall in this loop. Okay, I am putting delta small s inlet to outlet to equal to 0 and then I am solving, and finally you will be coming here, because whenever I am having a perfect gas which is undergoing isentropic expansion or isentropic process, this is the relation which I am going to get between temperature and pressure. Tp power 1 minus gamma upon gamma is equal to constant. So Pi power 1 minus gamma upon gamma is equal to PO power 1 minus gamma upon gamma. Can I find the TO from here? Can I find the actual temperature at the outlet of turbine if you are having isentropic expansion? Look at here. This formula you can apply only. Look at here. Don't be confused. This is the formula which you need to apply only. This formula is coming from here only. If you are writing Cp ln TO by Ti minus R ln PO by Pi, if you are solving it, you will be coming over here. Basically here. This you need to apply when you are having the perfect gas. This you need to apply when you are having the perfect gas, which is undergoing which process? Which is undergoing isentropic process. So what is the value of TO we are going to get, beta? TO is equal to what? TO will be equal to Pi upon PO whole power 1 minus gamma upon gamma into Ti. So TO is equal to Pi by PO. What is the Pi? 600 kilopascal by PO 300 kilopascal. One minus gamma, air na, diatomic gas I am assuming, into Ti. Ti is how much? 900 Kelvin. So can you tell me, if I am having isentropic expansion of the air, what is the temperature at the outlet? What is the temperature at the outlet of the turbine? What is the value of TO I am getting, beta? 738. Fantastic question. 738.377 Kelvin. So if I'm having isentropic expansion of the air, this is the temperature which we can have at the outlet of turbine. We cannot have below this. That is the reason why here this 480 Kelvin is coming impossible. Minimum temperature which is possible if I am having isentropic expansion of air in this given turbine is 738.377 Kelvin. Very good, Jyoti, very good beta. Now, which option is correct? Which statement is correct? C is correct or not? Yes, C is correct. C is correct. Now, in statement D, what he is asking, if air is assumed to undergo isentropic expansion in the turbine, the power developed by the turbine is. If you want to find the power developed by the turbine, what you need to do? If you want to find the power developed by turbine, what you need to do? You will be applying the steady flow energy equation because we are having a steady flow. So according to SFEE, according to steady flow energy equation, what can I write? If I am writing in rate form, it is a Q dot is equal to W dot CV plus delta KE dot plus delta PE dot plus delta capital S dot. But he is asking in per unit mass, so let me write per unit mass form. Small q is equal to small WCV plus delta small ke plus delta small pe plus delta small h. Now, I'm having well insulated turbine. If I'm having well insulated turbine, this small q is shunya. Neglecting the changes in kinetic energy and potential energy, this is shunya. So from here, what I'm getting, beta, small WCV is equal to delta minus का of course minus delta small h. So minus small ho minus small hi. So can I say this is basically what? Small WCV is equal to minus PP TO minus TI. Small WCV is equal to minus 1.005 TO minus TI. What is a TO? We have calculated 738.377 minus 900. Can you tell me? What is the answer we are getting, beta? Of course, it has to come positive. 162.431 kilojoule per kg. Are you getting this? Achha, can you tell me why we are getting positive value, not negative value? Arey, this is your turbine. Manohar, this is your turbine. Majhi, this is your turbine. So, control volume work has to be positive. Statement D is also correct. So what is the answer? BCD. BCD. Did you enjoy this question? Yes, sir. This was beautiful question. We have enjoyed this. Sir, what a beautiful question. Sir, what a beautiful question. Yes, yes. Very good, Sukumar. Chalo. Now, this is again one of the important topic. If examiner wants to make the paper little difficult, he will be touching this. Calculation of exergy destruction. You should know how to calculate the exergy destruction for closed system. How to calculate the rate of exergy destruction for closed system which are operating under steady state. You should know how to calculate the rate of exergy destruction for open system, basically control volume. Now, let us have one beautiful question. NAT, numerical answer type question, 1 mark. Numerical answer type question, 1 mark. And it is based on rate of exergy destruction, basically exergy destruction. Air enters a well insulated compressor operating at a steady state at 1 bar and 17 degrees Celsius with a mass flow rate of 0.3 kg per second. I am having a well insulated compressor The pressure at the inlet is given 1 bar, temperature at the inlet is given 17 degrees Celsius, 273. If you are adding, you will be getting 290 Kelvin with the mass flow rate of 0.3 kg per second. Air exits the compressor at 3 bar and 147 degrees Celsius. So PO is given 3 bar and TO is given 147 degrees Celsius. If you are adding 273, you will be getting 420 Kelvin. The exergy destruction rate within the compressor is a dash kilowatt, round off to 2 decimal places. First, let me write the data carefully for you people. Then we will think how to solve this question. Air enters a well-insulated compressor operating at a steady state at 1 bar and 17 degrees Celsius. PI is given 1 bar. TI is given 17 degrees Celsius. If I am adding 273, it will become a 290 Kelvin. With a mass flow rate of 0.3 kg per second. Mass flow rate is given 0.3 kg per second. Now, air exits the compressor at 3 bar and 147 degrees Celsius. PO is given 3 bar and TO, temperature at the outlet of the compressor, TO is given 147 degrees Celsius. 147 degrees Celsius. If I convert into Kelvin, add 273, 420 Kelvin. Okay. The exergy destruction rate within the compressor is I need to find within the control volume. Basically, I need to find. I'm not drawing compressor. You know how it looks like, right? He is asking in kilowatt, round off to 2 decimal places, and of course, environmental temperature of the ambient he has given in the question, which is 17 degrees Celsius, which means basically 290 Kelvin only. Now, what is coming in your mind? How to solve this question? What is coming in your mind? How are you going to approach this question? Very good, Roshan. How are you going to approach this question, beta? How are you going to approach this question? Can I say I'm going to write like this? Rate of exergy destruction, he is asking within the control volume within the compressor is equal to ambient temperature TD into rate of entropy generation within the control volume. So now the entire thing is depending how to calculate the rate of entropy generation within the compressor. The moment you are getting the rate of entropy generation within the compressor, just multiply by TD, which is basically 290 Kelvin, and you will be getting the answer. Now the question is how to calculate the rate of entropy generation within the control volume. Yes, according to entropy balance equation for control volume for open system. According to entropy balance equation for open system. What is the entropy balance equation for open system? Look at here. Rate of entropy change of the compressor plus delta S dot of the air fluid from inlet to outlet is equal to rate of entropy transfer along with the heat transfer plus rate of entropy generation within the control volume. Look at here. Out of these 4 terms, 2 terms will be Shunya. Anyone in the class can tell me which 2 terms will be Shunya? Air enters a well-insulated compressor operating at steady. The moment in the question you are having a steady state, the moment you are having a steady flow, this rate of change of the entropy within the control volume will be Shunya, because entropy is a property. So it has to be Shunya. The moment you are having well-insulated compressor, the rate of entropy transfer will be Shunya. So from here I am getting, if I want to calculate the rate of entropy generation within the control volume, that must be equal to delta S dot F from inlet to outlet. Now, rate of entropy generation within the control volume, mass flow rate into delta small s of the fluid inlet to outlet. So rate of entropy generation within the control volume is equal to m dot. Here I am having Cp ln TO by Ti minus R ln PO by Pi. Let us calculate the rate of entropy generation within the compressor within the control volume. What is the mass flow rate given in the question? They have given the mass flow rate. Mass flow rate is 0.3 kg per second. Cp of air, you must remember 1.005 kilojoule per kg per Kelvin ln TO by Ti. What is the TO? 420 Kelvin. What is the Ti? 290 Kelvin. 420 Kelvin by 290 Kelvin minus capital R 0.287 kilojoule per kg per Kelvin ln PO by Pi. What is the PO? What is the PO? 3 bar. What is Pi? 1 bar. 3 by 1. 3 by 1. So what is the rate of entropy generation I am getting within the control volume within the compressor? What is the rate of entropy generation we are getting within the control volume? Anyone in the class can type in the chat box. What is the capital S dot G within the control volume? Can I say 0.01? 0.01 708 kilowatt per Kelvin. Please confirm me this part. Please confirm me this part. If you have solved, can you confirm this part? Yes, rate of entropy generation within the control volume is coming 0.01708. Yes, beautiful, beautiful, Manohar. Sanjay, excellent. Jaswant, very good. Now I need to calculate rate of exergy destruction. What will be the rate of exergy destruction? Look at here. Rate of exergy destruction will be temperature of the ambient. Of course, I want to find within the control volume. Let me write that part also. Rate of exergy destruction within the control volume is temperature of the ambient into rate of entropy generation within the control volume. So rate of exergy destruction within the control volume is coming 290 and 2.01708. So in kilowatt, what is the rate of exergy destruction within the compressor I am getting? After solving this, what is the value I am getting, beta? 4 point. Yes, Santi, very good. Mohit, very good. Manohar, Gio Lala, 4.95. 32, 4.9. Yes, Mayank, very good. 4.9532 kilowatt. What a beautiful question. Yes, you need not to afraid of exergy questions. You need not to afraid of exergy questions. If they are asking exergy destruction, they are asking rate of exergy. That's how you can calculate. So answer of this question is 4.95. Answer of this question is 4.95. And the range is 4.65. Yes, Bharat, 4.65 to 5.25. This is the range. This is the range. Now I'm moving to next important topic, which is basically Gibbs relation, Maxwell relations. I'm moving to next very important topic. I'm telling you, you can expect the question from here. You can expect the question from here. Gibbs or Maxwell relations. Very important topic. Gibbs relation, Maxwell relation. Yes, you can expect some question from here. Let me match the size also. Yes. Gibbs and Maxwell, very important, very important. Let us discuss one question. Oh my god, Pritam, look at here. MCQ, 2 marks. Small g, what is this small g? Specific Gibbs function minus a t dou small g by dou small t at constant pressure is equal to. What a beautiful question. So basically in this question, what you have to do is first you have to see what is the expression of dou small g by dou t at constant pressure. You substitute here, then you will be able to figure out what is the correct option. So look at here. Look at here. He is asking what is g minus t dou small g by dou small t at a constant pressure. This is what he is asking in the question. So first we have to find dou z by dou t at constant pressure, and I am giving you one thumb rule. Look at here. Look at here. I have told you. Look at here. I have told you. This square, this Nagy square. Great. Pritham Pyares have studied under very fine teachers of Team Drona. Now, whenever you are having this situation where this term, middle term by some of the adjacent term, of course in partial difference at constant another term, another adjacent term, then what you need to do is, in such case, whenever you are having this situation where you are having the middle term on the numerator of the partial difference and one of the adjacent term in the denominator of the partial difference and at constant another adjacent term, you have to write like this. You have to write like this. Look at here. Small g is the function of what? Temperature, comma, pressure. Of course, according to state postulate, I can write like this. Small g is the function of temperature, comma, pressure. So what I'm getting? D small g is equal to dou small g by dou t at constant pressure dt plus dou small g by dou p at constant temperature dp. This is equation number A. Now what I'm going to do is I'm going to write one of the Gibbs relation. You know how to write the Gibbs relation. With the help of this Nagy square, I'm going to write one of the Gibbs relation where I'm having d small g on the left hand side and I will be getting the answer. Look at here. What is the Gibbs relation? I'm going to write where I'm having d small g on the left hand side. So d small g according to Gibbs relation, what I'm getting, beta? I'm getting d small g is equal to, what are the adjacent terms? T and P. So here I'm going to get dt, here I'm going to get dp. What is the diagonally opposite of dt? Small s. What is the diagonally opposite of p? Small v. Right? Now, arrow is coming towards t, so this is negative. Arrow is going away from p, this is positive. This is equation number B. And basically what I'm trying to tell you is, can I write this from equation A? From equation A and equation B, if I compare the coefficients of dt, can I say I got the value of dou small g by dou t at constant pressure and it is coming minus s? Are you able to understand this part, beta? Are you able to understand this part? I hope each and everyone is able to understand this beautiful part. He can ask you for 1 marks. In the exam, he can ask you for 1 mark that what is the value of dou small g by dou t at constant pressure? Answer will be minus s. Answer will be minus s. Anyways, this question is for 2 marks. You have to substitute this over here and let us see what are we going to get. I need to find the expression of small g minus t dou small g by dou t at constant pressure. So g minus t, this is a minus s. So g plus ts, t small s of course. Now look at here. Are you able to recollect? G is equal to Gibbs function is equal to enthalpy minus a T capital S entropy. So specific small g is equal to small h minus a T small s. So can I say G minus will be coming to the left hand side, it will become plus G plus a T small s is equal to small h. So can I say the answer is specific enthalpy? Answer is, what a beautiful question. Answer is B, Bombay. If you are able to solve this question along with me, if you are able to solve this question along with me, make the entire chat box red. What a beautiful question, I'm telling you. What a beautiful question. First, what you need to do is, you have to evaluate what is the dou small g by dou T at constant pressure. You know how to evaluate. First, you will be writing small g is the function of temperature comma pressure. Then you will be writing the Gibbs relation, and from there you will be comparing the coefficients of dt. Dou small g by dou T at constant pressure will be coming minus s. You have to be aware of Gibbs relation. If you have attended my crash course, you are aware of this, how to write the Gibbs relation, right? This is what I'm getting. Now, I substituted minus s over here. So I'm getting G plus a T small s, which is basically specific enthalpy. Now, look at here. I don't know. This is again very important topic where you are having wet vapor, you are dealing with the wet vapor, where dryness fraction is coming into the picture. You have to calculate the specific volume of wet vapor, you have to calculate the specific enthalpy of wet vapor, you have to calculate the specific entropy of wet vapor. Such question can come in examination. You are aware small v is equal to small vf plus x small vfg, small h is equal to small hf plus x small hfg, small s is equal to small sf plus x small sfg. Such questions can come in examination. Note down, this is a very important topic. Dryness fraction. Now, of course, I will be giving you little complicated question. Look at here, NAT. Numerical answer type question. Steam enters a turbine steadily at 3.447 megapascal and 455 Kelvin, where small h is given, small v is given, and leaves as wet vapor at a 5.5 kilopascal, where small hf is given, small hfg is given with a quality means dryness fraction only of 0.93. Okay, the power developed by the turbine is 11.185 megawatt, while heat transfer from the turbine to the surrounding occurs at a rate of 733 kilowatt. So basically W dot CV is given 11.185 megawatt and Q dot is given. Tell me one thing, when we are going to write the value of Q dot, will be writing positive or negative? 100% we will be writing negative, because it is a heat loss from turbine to the surrounding minus 733 kilowatt we are going to write. The volumetric flow rate of the steam at the inlet of the turbine is a dash meter cube per second, round off to 2 decimal places. Neglect the changes in kinetic energy and potential energy. Let me try to draw the diagram so that you can understand each and everything. I will be writing the data and then we will be seeing how to solve this question. Look at here. Let me say this is the turbine. Let me say this is the turbine. With this red dotted line, I am representing the control surface. And of course, the region in space which is under observation is my control volume. Let me say this is inlet, this is outlet. the rate at which work is produced by the turbine is W dot CV. The rate at which heat is rejected from the turbine casing is a Q dot. Now, what is the data given in the question? Let me write. Steam enters a turbine steadily. Steadily steam is entering at 3.447 megapascal. PI is given 3.447 megapascal and 450 Kelvin. So temperature at the inlet is given. How much? 445 Kelvin. Small HI, specific enthalpy at the inlet is given. How much? 3157.5. 3157.5 kilojoule per kg. Specific volume at the inlet is given 0.09 meter cube per kg and leaves as a wet vapor at 5.5 kilopascal. At the outlet state is a wet vapor. At the outlet state is wet vapor, and the pressure at the outlet is given. How much? Pressure at the outlet is given 5.5 kilopascal. 5.5 kilopascal. Small HF at this pressure is given. Small HF at this pressure is given 139.55 kilojoule per kg. Small HF is given. Small HFG is given. How much is small HFG? Small HFG is 2325.89. 2325.89 kilojoule per kg. At this 5.5 kilopascal dryness fraction at the outlet is given. Of course, if I am having wet vapor, it will be having some dryness fraction. XO is given 0.93, which is correct only. The power developed by the turbine is 11.185 megawatt. W dot CV is given. How much? 11.185 megawatt. If I convert into kilowatt, it will be 11185 kilowatt. Now, while heat transfer from the turbine to the surrounding occurs at the rate of 733 kilowatt. So, Q dot is given, of course, negative because heat loss na minus 733 kilowatt. The volumetric flow rate, the volumetric flow rate of the steam at the inlet of the turbine is. What will be the volumetric flow rate of the steam at the inlet? How many of you are able to understand? If the cross-sectional area at the inlet is AI, velocity at the inlet is CI, this AI, CI is representing the volumetric flow rate. Habib, very good. Roshan, very good. Can I say the volumetric flow rate at the inlet will be AI, CI? Basically, he is asking what is this discharge which is entering the turbine. Basically, he is asking volumetric flow rate at the inlet. AICI he is asking. Now, how to find this AICI? Look at here. Look at here. One thing I am able to understand. He is asking AICI in meter cube per second. Now, the question is how to calculate this. I will be telling you. But let us go to the basics. What is the formula of mass flow rate? What is the formula of mass flow rate? The formula of mass flow rate is, if I apply at the inlet rho I, AI, CI, I need to calculate the product of AI and CI. AI, CI is equal to density, I can write as 1 by specific volume. Na? So, M dot I is equal to 1 by small VI, AI, CI. Now, can I say AICI, the volumetric flow rate at the inlet is how much? M dot I small vi. Now small vi is already given in the question. Small vi, specific volume at the inlet, is given in the question. There is only one thing which is unknown. There is only one thing which is unknown, m dot I. If somehow I can calculate what is the mass flow rate at the inlet, I will be able to calculate the volumetric flow rate at the inlet. How to calculate the mass flow rate at the inlet? Anyone in the class can tell me how to calculate the mass flow rate? For that we have to apply the steady flow energy equation. For that we have to apply the steady flow energy. That is the reason why he has given W dot CV, he has given Q dot. By applying the steady flow energy equation, we will be getting m dot, and that m dot we are going to substitute over here. So can I say, according to SFEE, according to steady flow energy equation, what I'm having, look at here, beautiful, beautiful. According to steady flow energy equation, Q dot is equal to what? W dot CV plus delta KE dot plus delta PE dot plus delta capital H dot, neglecting the changes in kinetic energy and potential energy. So this term is a shunya, this term is shunya. Can I write? Q dot is equal to W dot CV. Where is m dot? Yes, m dot is hidden over here. M dot small ho minus small hi. Now look at here, beta. Q dot is known, W dot CV is known. Q dot is known, W dot CV is known. M dot I need to find, small hi is known, small ho is unknown. Can you tell me, beta? Can you tell me how to find small ho? How to find the specific enthalpy at the outlet of the turbine? This is the beauty. Here you have to apply the concept how to calculate the specific extensive properties of the wet vapor. Small ho, how to calculate small ho? At the outlet I am having wet vapor, that will be equal to what? Small hf plus xo, small hfg at the outlet pressure, because at the outlet you are having wet vapor, so you have to apply this formula to calculate the specific enthalpy at the outlet. Now small ho is equal to, what is the small hf given in the question? 139.55. 139.55 at pressure PO, which is basically 5.5 kilopascal. XO 0.93 into small HFG. What is the small HFG, beta? What is the small HFG? 2325.89. 2325.89. And from here, what is the specific enthalpy at the outlet we are getting? What is the specific enthalpy at the outlet we are getting? Can you tell me what is the specific enthalpy at the outlet we are getting? 2302. 2302 point how much? 6277. 6277 kilojoule per kg. This is my small HO. This is the specific enthalpy at the outlet of turbine. Specific enthalpy of wet vapor. The moment I got a small HO, now there is nothing. I will be substituting a small HO over here and I will get the value of m dot. So look at here. Q dot is how much? Q dot is how much? Minus 733 kilowatt. Minus 733 kilowatt is equal to W dot CV. W dot CV is how much? W dot CV is given in the question. 11185 kilowatt. 11185 kilowatt plus m dot small ho 2302. 2302 point how much? 6277. 6277 minus small hi. What is the value of small hi given in the question? 3157.5. 3157.5. 3157.5. If we are solving this, we'll be getting m dot. What m dot will come? Minus 733 minus a 11185 divided by how much? 2302.6277 minus 3157.5. So what is the value of m dot we are getting? Mass flow rate of the steam. What is the mass flow rate of the steam? 13.9413. 13.9413 kg per second. This is the mass flow rate of the steam we are getting. This is the mass flow rate of the steam we are getting. The moment we are able to calculate the mass flow rate, the volumetric flow rate, AI small ci at the inlet is, of course, I'm having a steady flow. This m dot is basically m dot I only. M dot I into small vi. M dot I into small vi. 13.9413 into small vi, which is given in the question. What is the small vi given in the question? 0.09. 0.09. So what is the volumetric flow rate we are getting? What a beautiful question. Oh my God. Here you are applying the steady flow energy equation. Here you are calculating the specific enthalpy of wet vapor. Oh ho ho. 1.2547. 1.2547 meter cube per second. Are you getting the same answer? What a beautiful question. What a beautiful question. Are you getting the same answer? 1.2547. How many of you are getting? Nishant, Aditya, Manohar, oh ho ho, Bhana, Mayank, Sant. Oh my God. Subha, very good, very good. 1.2547. 1.2547, round off to 2 decimal place. So I'm giving the answer 1.25 and the range is 1.05 to 1.45. Now, according to me, there is one more important topic. Chiru, very good, beta. According to me, there is one more topic which is very important. Clausius-Clapeyron equation. Clapeyron equation or Clausius-Clapeyron equation. This is very important. This is a very important topic. Clapeyron equation and Clausius-Clapeyron equation. Very important. Let us solve one question on the basis of this particular important topic. Oh my God, MSQ. I have framed a number of MSQs for you. MSQ, 2 marks. MS, each and every question, whatever we have discussed is the brand new question. MSQ, 2 marks. Ankit, very good. A piston cylinder arrangement contains 1.5 kg of a refrigerant. I'm having a refrigerant which is having the mass of 1.5 kg initially at 200 kilopascal and minus at 10 degrees Celsius in a saturated liquid state. I'm having a piston cylinder arrangement. There is some refrigerant inside the piston cylinder arrangement whose mass is 1.5 kg. The pressure of the refrigerant is 200 kilopascal and the temperature is minus at 10 degrees Celsius, basically 263 Kelvin, and the initial state is saturated liquid state. The state of the refrigerant is converted from saturated liquid to saturated vapor by supplying 310 kilojoule of heat at constant pressure. What we are doing is we are supplying the heat at constant pressure, because of which what happened, the state of the refrigerant converted from saturated liquid state to saturated vapor state. How much heat we have supplied? 310 kilojoule at constant pressure. During this process, the volume of the refrigerant increases by 0.15 meter cube. Of course, volume will be increasing because saturated vapor will be having more specific volume as compared to saturated liquid. So yes, a change in volume, increase in volume is given 0.15 meter cube. Which one or more of the following statements are correct? What he is asking is specific entropy change during this process of the phase change from saturated liquid to saturated vapor. He is asking again in statement B, specific entropy change. In statement C and statement D, he is talking about the slope of the saturation curve on PT diagram. First of all, I will be trying to draw the diagram so that you can understand. Look at here. I'm drawing the TS diagram. I'm drawing the TS diagram where on the vertical axis where on the vertical axis I'm keeping temperature. I'm drawing the TS diagram where on the vertical axis I'm keeping temperature, on the horizontal axis I'm keeping specific entropy. Let me say dome is something like this. Look at here, there is some isobar. Yes, this is the isobar. This is the isobar. Now, according to the question, initial state is this: saturated liquid state at a pressure 200 kilopascal. At pressure 200 kilopascal. Now, what we have done is we have supplied the heat at constant pressure, because of which what happened, this saturated liquid state converted into saturated vapor state. Now, during this phase change, I have to find what is the entropy change or specific, what is the specific entropy change for this phase change process, and then I have to find the slope of saturation curve on PT diagram for this saturation state, where pressure is P and temperature is T saturation. Temperature is T saturation, which is given in the question as minus 10 degrees Celsius, 263 Kelvin. So let me write the given data. A piston cylinder arrangement contains 1.5 kg of refrigerant. So mass of refrigerant is given 1.5 kg. Mass of refrigerant is given 1.5 kg, initially at 200 kilopascal and minus at 10 degrees Celsius. P is given 200 kilopascal, and of course corresponding saturation temperature is given minus 10 degrees Celsius, which means, if I'm adding 273, which means 263 Kelvin. Fine. Initial state is given saturated liquid state. Now what he's saying, please listen carefully. The state of the refrigerant is converted from saturated liquid to saturated vapor by supplying 310 kilojoule of heat at constant pressure. So final state is a saturated vapor state. And in order to get this saturated vapor state from saturated liquid state, we have supplied the heat of 310 kilojoule, of course at constant pressure. During this process, the volume of the refrigerant increases by 0.15 meter cube. So capital B1 to 2 is given 0.15 meter cube. Now, what he is asking in the question? He is asking a specific entropy change is. Look at here, beta, if I am having a closed system undergoing internally reversible process at constant pressure, you know the change in entropy can be written as Q by T. Here, this temperature is saturation temperature. So delta capital S from initial state saturated liquid state to final state saturated vapor state is a Q by T is a T saturation. When can I apply this formula? What are the conditions for applying this formula? Look at here. Whenever we are having some closed system, which is undergoing some internally reversible process, at constant temperature, then I can write entropy change is equal to Q by T. Yes, during the phase change, I'm having closed system. I'm assuming phase change is internally reversible process, and of course, constant temperature is saturation temperature. So from here, if I want, since I need to find the specific entropy change, mass into delta small s 1 to 2 is equal to what? Q by T saturation. From here, what is the delta small s 1 to 2 I'm getting? If I want to write the expression of delta small s 1 to 2, this will be equal to, look at here, delta small s 1 to 2 will be Q, which is given in the question, mass, which is given in that question, T saturation, Q divided by M T saturation. Let us find delta small s 1 to 2 from saturated liquid state to saturated vapor state. This is given 310 kilojoule, M 1.5 kg, T saturation 263 Kelvin. Can you tell me what is the delta small s 1 to 2 we are getting, beta? What is the delta small s 1 to 2 we are getting from here? 0.7858. 0.7858, of course, kilojoule per kg per Kelvin. This is the specific entropy change when the phase of refrigerant is changing from saturated liquid to saturated vapor. 0.7858, 0.7858, 0.78, yes, 0.7858. Statement A is correct, statement B is wrong. Now, anyone in the class, Mehtab, Sanjay, very good. Slope of saturation curve on PT diagram. How to find the slope of saturation curve on PT diagram for the given saturation state? You remember there is something called Clapeyron equation. What is that? dP by dt of the saturation curve at a given saturation state is 1 by T saturation small hfg divided by small vfg. अगर मैं मास से मल्टीप्लाई कर दूं न्यूमरेटर और डिनोमिनेटर में, dP by dt of the saturation curve for the given saturation state on this PT diagram, मास से मल्टीप्लाई करूंगा तो ये क्या हो जाएगा? कैपिटल HFG डिवाइडेड बाय कैपिटल VFG. ये कैपिटल HFG क्या है? अरे चंपू, वट एवर कैपिटल Q इज गिवन दैट इज कैपिटल HFG ओनली ना. वट इज whatever delta capital V1 to 2 is given, that is your capital VFG. अरे ये capital VFG का मतलब क्या है? VG minus VF. What is VG? Basically V2. What is VF? V1. Because final state is saturated vapor, initial state is saturated liquid. तो V2 minus V1 is basically your VFG only. तो यहां से मेरे पास क्या आ गया? What I'm getting from here, dP by dt of the saturation curve for this given saturation state is 1 by T saturation Q by delta V1 to 2. Let us substitute the values. Champa, let us substitute the values. dP by dt of the saturation curve for the given saturation state is 1 by T saturation, 1 by 263, 310 kilojoule divided by delta V1 to 2. Delta V1 to 2 is how much? Delta V1 to 2 is how much? 0.15 meter cube. So if I solve this, I will be getting some number in kilopascal per Kelvin, because Q I have written in kilojoule and capital T I have written in Kelvin. Delta capital V1 to 2 I have written in meter cube. 7.858 kilopascal per Kelvin. Oh my god, oh my god. This is the slope of saturation curve for the given saturation state. So which option is matching? 7.858. Yes, C is correct. Re baba. D is wrong, re baba. So answer of this MSQ is A, C. How many of you enjoyed this beautiful MSQ? How many of you enjoyed this beautiful MSQ? Come on, everyone. I hope you enjoyed. Yes, yes, yes. Subha. Make the entire chat box red. Oh my god, I have given you the beautiful questions. Please take this PDF. I'm telling you, whatever the important topics I have written here, please solve some more questions. And yes, you know, we are going to meet again on 14th. We are starting the Super 30 series where me and Vinod sir, yes, get All India Rank 1 XE and get All India Rank 1 Mechanical, we will be discussing the beautiful 30 questions of thermodynamics and applications of thermodynamics. You are preparing for mechanical, you are preparing for XE. You should not miss the session on 14th. Day after tomorrow, day after tomorrow 7 p.m. on Gate Wallah MECEXE channel, and that will be in English. वो इंग्लिश में होने वाला, जहां पे हिंदी और इंग्लिश आपके लिए मिक्स कर दी जाएगी रे बाबा. So look at here. Again, I'm telling you the important topics. Again, I'm telling you the important topics which I have given you. Please solve these. Please solve these. First important topic which I have given you, work interaction, displacement work interaction for various standard processes. This is the important topic number 1. Important topic number 2 which I have given you, heat interaction for various standard processes. Important topic number 3 which I have given you, study flow energy equation, its application for nozzle. Study flow energy equation and its application for turbine. Then study flow energy equation and its application for mixing chamber. Then combination of heat engine and refrigerator. Combination of a heat engine and heat pump can come in the examination. Then I told you, you can have the question on Clausius inequality. Then how to calculate the entropy change if I'm having some perfect gas which is undergoing some process. Then calculation of entropy change for incompressible substances. In this particular case, we were having the constant specific heat. Then entropy balance equation for open system, very, very, very important nowadays. From here, we are getting lots of questions. Exergy destruction. If you are having some closed system, you should know how to calculate the exergy destruction. If you are having closed system undergoing steady state operation, you should know how to calculate the rate of exergy destruction. For open system, for control volume, you should know how to calculate the rate of exergy destruction. Gibbs relation and Maxwell relation, very, very, very important. Gibbs relations and Maxwell relations, very, very, very important. Concept of dryness fraction. Oh my God, you can have some question from here. Then Clapeyron equation, Clausius-Clapeyron equation, very, very, very important topic. So my friends, tomorrow Approved sir is going to take engineering mechanics Saturday 14th of January, and this series will be getting ended on 29th of January. This is the schedule. If you want to take the screenshot, take the screenshot. If you want to take the photograph, you can take the photograph. This is the schedule which you are going to have. I have taken my part. Then Approved sir, Vishal Soni sir will be live, the legend of engineering mathematics. Oh my God, you should not miss. 2 p.m. to 4 p.m. Swadesh sir, Vinay sir, Ramanand sir, Amulya Ratan sir, Amit Dixit sir, Viswajit sir, Amit More sir. Oh my God. Yesterday only Aditya Pal sir has taken 11 hours PYQ session. Approved sir, Sandeep sir. This team is beautiful. पढ़ाने देश का कोना कोना आ गई है टीम द्रोणा. महा रिवीजन कब से स्टार्ट होगा? महा रिवीजन बेटा 20 तारीख से स्टार्ट होगा. डोंट वरी, महा रिवीजन आल्सो वी आर गोइंग टू टेक. एक्सी के लिए और एक्स्ट्रा, डोंट वरी, आई हैव प्लान्ड फ्यू थिंग्स. I will be telling you. Let us first complete this part where mechanical is also there. सब होगा प्रभात महा रिवीजन में, पूरा होगा. डोंट वरी अबाउट दैट पार्ट, वी आर गोइंग टू हैव. अच्छा, डिड यू एंजॉय द क्लास इन इंग्लिश? जनरली यू पीपल आर नॉट हैबिचुअल ऑफ क्लास इन इंग्लिश, राइट? Generally, you people are not habitual of class in English. Did you enjoy the class in English? Did you enjoy the class? Champu was thinking, Arre Champu, in last 7 years, I'm settled in Vizag only. I'm taking class at my institute. Yes. We don't know how sir is going to teach in English. My delivery is better in English as compared to Hindi nowadays. Chukka Sravant Kumar, please launch GATE batches in English. But it's already going on. Jhamhare Baba. Chalo. Thank you so much. Love you all. Take care. God bless you. Thank you so much, beta. Thank you so much. Thank you. Love you all. Take care. Thank you.